Jen is also hanging out.
Hi.
So, today we are going to work on the Live2D Physics engine, which I pretty much finished reverse engineering on the last stream. And so this time we need to implement something, but I don't want to implement the original version because it's very janky. So I want to implement something a little bit more. Okay, I am getting really tired of my eyes always being so closed. I think it's the tracking, but I'm just gonna cheat right now and change it ad hoc because
I think it's good.
It's too no, my eyes are too closed right now.
I think it shows your character.
My character? No, it's way too.
Like total. A little bit.
Nah, a little more. See, like that's better. That's more like it.
Okay.
So I'm not so sleepy all the time. Okay. Yeah, we're gonna work on the physics engine because we figured out how it works on the last stream. And actually, I didn't mention this, but when we did the Godot thing in our Tokyo Hacker Girls, so please subscribe to Tokyo Hacker Girls.
Hi.
Hey, please subscribe to Tokyo Hacker Girls.
Hi.
Put it in the chat. Is it link? Oh, YouTube does not link. Okay, great. Oh, hold on. Yes.
What are we hacking today?
We're gonna put this one in like
Physics.
that. I'm gonna do that.
Why am I here?
And do some magic. Okay, and I'm gonna pin this message so people see it. Alright, there we go. So, we have the engine, and I didn't mention it, but when we did the Tokyo Hacker Girls debut with together, we did a Godot little game, and that was using Ayagami. Which is all the work I've done. And since the physics engine was not implemented yet, what I did was I took my Python, like reference implementation of the original, and I did a horrible hack where I had a script running on another computer, taking the tracking data, applying physics, and sending it over to Godot. It did work, which proves that it does actually work as intended. So now we need to take that and implement it somehow. And it's going to be interesting because I don't want to implement it one-to-one because it is kind of terrible. I want to implement it, I want to implement a new version that behaves better and then add fudge factors to make it behave similar to the broken version, to the original version, so that, the physics generally looks the same for the most part on existing models. But it behaves better. It behaves better with different frame rates and things like that. So I want it to be more reliable and better behaved, which means it has to be different to the original. But I want to come up with a version that behaves close enough to the original and can be adjusted to be close enough to the original. And so we're going to use that. That's the plan for today, which means we're going to be doing math.
Math. I like math.
You like math? So, yeah, let's, I think we can pretty much get started. Okay?
Hi.
Can I save your position here? This is, hold on, here. So, there we go. Alright. I think we are a little overlapping right now. Oh, you should be under me.
I'm so small.
Why are you on top of me?
What is this?
You should be under me. Yeah. Okay. Yeah, I guess I should be a little to the left if we're going to do this more often. Or should I put you to my left? No, because then it's kind of backwards, right? I should put myself to the left. Like that. Yeah, I should put myself here, and then you can be over here. How about this?
I'm so small. I'm
You're
like
small.
a baby.
You're like a baby.
Why
You
can't
wanna be
I
bigger?
be bigger? I
Okay.
want to be bigger.
How about there? So you're a little behind me, right? So
Okay, yeah, I'm far away.
that's good.
Okay.
You good there?
Okay.
Okay, let's see.
Yes, mommy.
Record position, and I guess I might as well put myself in there.
What is Lena on top moment? I'm always on top. What's that smile?
All right, there you go.
Okay.
So,
Math. Lena's on my
math. Yes, so this is not where I want to be yet because I don't want to be doing that. So let's clear this out.
I guess I
And
need to see your screen.
yeah, you probably need to see my screen, right?
Right.
Okay, let's go here. You need to see my screen because you're like, oh, I want to see my screen, but I'm like, you're gonna be working with me. Why do you want to see your screen?
See, do this American.
Okay. So we are in Dev Mach 3 RE, and so the physics engine is the simulator here. Did I put my iPad? Yeah, I did put the physics stuff here. Okay, so let's open up the physics engine and the iPad notebook. Oh, not like that. How do I do this? Jupyter. I think you just do Jupyter Notebook and then can you pass the notebook to open it?
Oh my god, Jupyter Notebook?
Yeah, we're gonna use Jupyter Notebook.
Oh god.
Just probably just open it.
Demonstrate math and physics and then like pendulum and then... Oh wow, lovely. You're starting to sound like data science person.
Uh-huh. Oh wow, okay. This is
wow.
Yeah, that's fine. Okay. There we go. Okay, so this is what I was doing.
Okay, can you turn the OBS back on?
Yeah.
Thanks. It's hard for me to stay on the screen.
So I actually probably should do a little explanation of what's going on with Inkscape before we get there. So
what's Inkscape?
Just graphics.
Graphics. 小龙虾.
Why is this tiny? Weird moment. Alright. So
are you drawing?
I'm gonna do some scribbling to demonstrate.
はい。お願いします.
I cannot aim with my mouse today. This is small. Alright. So we have a pendulum, right? And make this up a grid. So we have our pendulum. And let's make it actually visible, make it red.
That's the ball?
Black.
Or that's the
pendulum.
Point.
That's the ball.
Okay, that's the ball.
Yeah.
One ball, not balls.
Too much. Okay, so we have one pendulum, right? And then we have the... Just put this here.
Can it be pink?
It can be some kind of pink. Maybe.
Like a coral?
Mean like that?
Bottom? Yep, okay. Better for the eyes.
I like this one.
Cute. Okay.
This one. There you go. It's cute.
Go on.
So we have the pendulum and you have the origin. Let's put it like this here.
Yeah.
Let's scale that for that. So there's our pendulum.
Okay. Well, you can make it move in this.
No, I can't make it move. But I'm just showing the diagram. Okay.
Okay, it's a pendulum.
Yeah.
It's a little small for the people.
I'm zooming. Okay. So the problem we have is a pendulum has momentum. So when it's moving in, like for example, it has like a
acceleration,
like a vector there, right?
Okay.
Like
a velocity vector.
Yeah, like a momentum, right? A velocity vector. Let's make this like, I don't know, some kind of blue or something. Something that stands up, but something that's
the same saturation. Go for it. Go down. Go down.
Yeah.
Oh god.
We have to make our physics diagrams pretty. Okay, how about that?
Oh god. Okay, fine. It's so girly. Okay,
I'll try this one. Okay.
So the momentum.
Yeah, so you have the momentum, right?
All right.
Now the problem is, if you're simulating a pendulum, the pendulum is going to be rotating, right? So I'm going to actually
you're not selecting the vector.
Yeah, I know.
Oh. You gonna rotate it?
Yeah. I don't know if I can snap that, but we're going to try.
Maybe.
Close enough.
Okay, good enough, yeah?
Close enough. So the thing is, a pendulum has a certain momentum, right? And let's say the momentum is kind of large or something like that.
Yeah.
So when it moves in an arc, right? It is moving.
A slice of pizza.
Yes, a slice of pizza.
This is what pizza.
I don't know if I can do that, but I can try.
The trace, the track is moving.
Yeah.
Okay.
I can probably make this work.
Are you like gonna do like a sine wave or something? Were you do like the music yesterday? I saw the sine wave and stuff, and it reminds you.
So then, yeah. So it moves in an arc like that, right?
So
now the problem is that and we can move this side here so it matches that one. Now the way you simulate a pendulum, because we are doing a simulation where this is not a real physics system. Real physics doesn't have frames. In simulations, we have frames. So if you want to simulate a pendulum reasonably accurately in code, what you do is you would calculate things based on because this is a rigid pendulum, right? This is a fixed length. There's no bounciness to it.
Okay.
Right?
Like a steel rod.
Yeah, or plastic or whatever, right? Because this is a rigid pendulum, the way you simulate this accurately is by storing the angular momentum of the ball, of the bob, is what it's called.
Okay.
Right? So this momentum, even though in xy terms, this has momentum in vector in this direction, it's moving in this at this point in the in the simulation in the state, this has a linear velocity in this direction.
Yeah.
Because the rod is a fixed length, what this really has is an angular velocity, right? What we really want to think about is in terms of the angle of the pendulum, and so this velocity is going to strictly make it move along this curve, because that's the only way it can move. If you simulate a pendulum this way, by basically storing the angular momentum and then increasing the angle in radians of the pendulum,
yeah,
then you get a very accurate simulation. The problem is Live2D doesn't do that.
Okay.
What Live2D does is this. Let's say the tip of the arrow here is the momentum, right?
Okay.
What it does is it says, okay, so we're going to simulate it as linear momentum. So we're going to say in the next frame, the bob actually moves here.
Huh.
Let's say, I can't snap it, but here it's close enough actually, yeah. So let's say in the next frame, the bob moves here, right?
Okay, in a fantasy world?
Yeah. And because it can't move there, right, then it gets moved back.
Yeah, like teleported.
Yes, it gets teleported to this position here, right? Now, if we do that, if we do this like teleport thing here, right, it looks like that, and make this center another color. This is not terribly accurate, but it's basically something like that, right?
Yeah. Then wouldn't the law of physics be like in another planet is not Earth?
Well, I mean, it is. The problem is not that it's. Not what I want to do. What I want to do is just move that here. So you get something like that, right? And the problem with this is, okay, we've moved the pendulum along the curve, like that. That's fine. Like the pendulum is moving.
Yeah.
But look what happened. This line and this line are not the same length.
No, they're not.
This curve is shorter, right, than this curve.
The momentum changed.
The momentum was lost.
Oh, yeah.
So the problem is the Live2D physics simulation, because it does this linear simulation and then, like clamping back to the angle of the pendulum to the length, it's losing momentum every single frame. Which means that even if you don't have any drag and you don't have any, any coefficient that is causing it explicitly to slow down, it slows down anyway.
So if we have like a pendulum kind of like a Live2D like rigged part, it's gonna stop by itself, even if like it's supposed to.
Even
keep
if
going.
you change the I forget what it's called, but one of the properties you set is basically the drag, right? Even though it's not called that. Even if you set it's not the drag. I think they call it the. Oh gosh, I forget. They use the worst terms in the world for the simulation. What did they call it? think it's mobility is what they call it, okay? Mobility is actually the inverse track. So if that's 1.0, it's not supposed to stop. It stops anyway. And the reason is this. The reason is that their simulation is in an XY world, and then every frame, you lose some momentum. And that also means that this line and this line are pretty far apart here, right? This is significantly shorter than here. But if we were to do it here, right? It'd be pretty close, right? So the faster it moves, the more momentum it loses.
Okay.
But also, the faster your frame rate, the more you divide down this simulation, the less it loses momentum. So now we have a momentum loss that depends on the frame rate, which is a bad thing. Because you want your physics to not depend on the frame rate for this kind of thing. Yes.
Chat, Suster mentioned about gravity. Do we assume there's no gravity in this situation?
No, pendulums do not lose momentum on the upswing.
Eh?
Oh, sorry. You mean, okay. Sorry, they do lose momentum, but that is a different thing. We do lose momentum due to gravity, but the energy is preserved. The kinetic energy is turned into potential energy, right? So we can, for what I just explained so far, we can pretend there's no gravity, and this is just rotating endlessly in a circle, okay?
Okay.
If you do that with Live2D, which you can set up that situation, it will slow down. So that's what we have now.
So the models are streaming from space. if the pendulum move forever.
Yes.
Okay.
So we are losing momentum, but specifically we are also losing energy. Okay?
Okay.
Because, well, that's different, but I mean, we're losing energy. So even if we are not considering gravity here, the pendulum is going to stop, which means that if we do consider gravity, we are essentially not moving as far as we should. Right? It was supposed to go further, and then gravity is supposed to bring it back. And so we are losing some momentum. And then we're going to also apply gravity to slow it down. What Live2D actually does here is basically it takes this, right? And then it says, okay, well, gravity is applying a constant acceleration downward. And since it can't go downward, right, it will like basically shift it further. So it will do something like... if you take this line, what Live2D is actually doing with the gravity, I can show you the code actually, it'll make more sense. What Live2D is doing, and this is the code we reverse engineered that is accurate, is it takes the position as a XY coordinate.
Okay.
It adds the velocity.
Okay.
Which is actually just the, how much is actually the difference between the previous step and the current step. So it's actually just it takes the previous position and the current position. It takes the difference, considers that it's velocity, and tries to continue it. Okay? And then it does this mobility thing, which even if it's 1.0, we are saying it's losing. And then it applies gravity, so it's actually just... it basically just moves it downward, right? So effectively what we have is Live2D is doing this... and then this, and we can take this, delete this, this is also complicated. It's the same thing, okay. It continues the previous motion, and then it does some gravity, and then, you know, it snaps back like that. That's basically what it's doing. If I make it a little more accurate. Okay, that's how Live2D is calculating this math.
Yeah.
And that's why it loses momentum.
So what's the problem
and
trying
energy.
to solve?
I don't want to use this simulation. This is terrible. If you simulate the pendulum in terms of angle and in terms of angular velocity, this problem doesn't happen. Okay, you're still reducing the angular velocity based on gravity, but you're not losing more velocity because of that. So this is a simulation of what happens. If I set, what is this thing?
Damp factor.
The orange is a simulation using an algorithm which uses radial velocity and angle. And this is the angle. Okay, what you're seeing in Y here is the angle in radians. Okay?
Okay.
The pendulum is swinging. It doesn't stop.
Mm-hmm.
The orange line, right?
Mm-hmm.
The blue line is the Live2D algorithm.
Okay. It stops.
It stops, right?
Mm-hmm.
So, and also the you can also see the frequency is a little off, right? Actually,
So snap.
even the frequency is a little.
It's not matching the.
Yeah, because of that
period.
damping, the period is also a little off, right?
Mm.
So we want to match this to Live2D as much as possible. Now, one thing that I did is this: if you apply an extra damping factor, basically.
Mm-hmm.
So if you add friction.
A friction.
If you add friction, you get something pretty close.
Okay.
Now, my question is this factor that I am adding actually accurate for different starting conditions? This is, you can see it's a little off, right? It starts in the same place, but then actually Live2D loses energy faster at the beginning and slower at the end. So this factor isn't quite what we want. The way Live2D is losing energy here is the faster the velocity, the more energy it loses. Because it's losing this like sine angle here, right? So I want to simplify this down to something that makes a little more sense. So we have this simple damping factor, which is V times the damping factor, right? One thing we could do is raise V to the power of something. So if we say V times 1.1, for example, so it has more effect at higher velocities. And that did not work. Invalid value and scalar power.
You're doing like a power of a V? Is it?
Hold on. I'm confused. What? Why would that not work? Now I'm confused. Do I have to use PAL? PAL? Math.pal?
Yeah. I remember I never used the...
I thought that worked, but I guess maybe it doesn't.
For some reason, I never used that.
Math domain error, great.
What's a math domain error?
Oh, maybe because V is negative? Probably because V is negative, right? So we need the, yeah. Okay.
Absolute value?
Yeah, we need the, okay, let's do...
ABS.
Damp equals, let's do it like this. V, it's ABS V. Is it sine or cn? I don't know if there's a sign. There's copy sign, right? Copy sign 1.
What is sign? Like the negative sign?
Yeah, it's copy sign.
What's copy sign?
It copies the sign, right? It's like taking ABS V to the power of 1.1, and then like take the original sign, right? Okay, so now we have something that you actually can see it's still not quite, right? Let's try 1.3.
So you're trying to...
I'm trying to make the line closer.
To Live2D.
Yeah. So I think this is actually kind of closer now, and then the factor is a little low.
You're reversing engineering their function, their pendulum function.
No, I mean we know what it is. Like we could try to solve this mathematically. We know that this is based on the sine, right? Like the angle, you take the angle, you take the cosine of the angle, and that is actually how much energy is lost. But I'm trying to avoid introducing like trigonometric functions into like my I mean, I guess I could do it. But because they're doing it for every frame, right? It's a little strange how it is lost.
Okay.
Because you basically have to do something like they lose the cosine of the velocity. Like the cosine is multiplied, the velocity is multiplied by the cosine of the angle, roughly, with the delta angle for every frame. But because this simulation is like not how do I put this? We are not running this at the original frame rate. We can just work at any frame rate, right? I'm trying to avoid introducing functions that like depend on the frame rate. If you have like the cosine of an angle and then the angle depends on the frame rate, then you're back to depending on the frame rate. Does that make sense? Like, yeah. I'm trying to approximate this with something that does not involve the original.
The angle change.
Yeah. So yeah. So we're actually getting kind of there, right? If you do 0.1, 0.2. So now it actually loses too much at the beginning and too little at the end, which means this power is too big. Now there are easier ways of optimizing this. Like you can definitely do a numeric optimization, but I want to come up with some values for now because this doesn't have to be exact. That just kind of look good enough, you know? So do a little manual kind of optimization here. So now this is getting kind of close, right? It actually starts a little high, then gets a little low, and gets a little high. So it's like it starts losing a little slowly, then loses a little too fast in the middle, and then in the end it kind of doesn't quite lose as fast in the end. So maybe this function is not what we want, right? Maybe it's not a power. So let me think about this. Now we're losing too quick at the beginning and too slowly at the end, which means this is still too big, I guess. Let's try 1.1 here. Okay, that looks a little closer. And now we're back to a little too much at the beginning.
Wait, this is the part of differential equation where I haven't get it yet.
This is actually the differential equation.
Oh really?
So
how is it differential equation?
So there's what was the name of this thing? Physics. The rota. This thing.
Wrong kuta.
This is the simulation algorithm that I'm actually using.
Okay. I'm glad I asked because I'm so lost. What's going on?
Okay, yeah. So this is the simulation algorithm that I'm using, and it works very well for this stuff. Okay. This is a numerical solver for differential equations. And in this case, differential equations, which sounds really fancy, and honestly, I kind of hated that class. What we really mean is that we are working in terms of the velocity and the acceleration instead of the position. Okay?
Okay.
So we are using the
derivative.
So the derivative of position is the rate of change in position, which is velocity. The derivative of velocity is just the rate of change in velocity is acceleration. Right?
Okay.
So what this solver is doing is it's taking our equations for acceleration and velocity and basically calculating how the system behaves over time and doing that in a way that is basically independent or, fairly accurate, even if you don't run it at a very high frame rate.
Okay.
Does that make sense?
It says physics stimulation, so it doesn't have to be pendulum.
No, this is actually this website is really nice. I actually really recommend this. myphysicstab.com. It has a ton of stuff.
Oh.
Like a huge amount of stuff.
Wow.
And everything here is you get you can play around with it.
Okay, remind me what's damping? Like
damping is how much it slows down. It's the friction basically.
Oh.
So if you add it, you can see that it slows down.
What's drive amplitude?
That's if you want to actually add, like, if you're moving it, kind of like that.
If the thing is moving itself.
Like if you're doing, it's kind of like a swing, right? It's like you're adding a
force, external force.
Yeah, and then you can make it like faster.
Okay.
Like
Can you stimulate if the ball is like a person, like you hang it up and then like the person moves and then stimulate how it moves? Is that too creepy?
What do you mean?
Like if you time it up on it, would you be able to stimulate how the string moves? Huh?
I'm confused.
No, I'm talking about like if the ball itself has like movements.
You mean like the ball is like moving, like
the move is a moving creature. Yeah.
Yeah. Well, I mean that's kind of what this is doing. The drive, right?
Okay.
Kind of.
Okay.
So yeah, this has like all the math, and it tells you like this is the differential equation, right? This is basically the second derivative of the angle, which is the angular acceleration, is minus g divided by r times the sine of the angle. So what this is saying is that if you look at the diagram here, the sine of the angle relative to this is 0, right, is basically going to increase as you go here, right, and then decrease towards 0. So that is how much gravity is affecting the pendulum. When the pendulum is at the bottom here, there's no effect of gravity. Okay. Because gravity is perpendicular to the axis of motion, right? So gravity at this point doesn't do anything.
Yeah.
When the pendulum is over here at 90 degrees, gravity is at its full strength, right? Yeah. So the factor there is the sine of the angle, right?
Makes sense.
So the acceleration due to gravity in terms of the angle of the pendulum is negative because it's slowing down as it goes up the sides, right? G is gravity divided by R, which is a factor based on the length.
It's the length.
Yes.
It's not a factor, right? It's just the length.
It's the length. And then the sine of the angle, right? So it's a very simple equation, right? And it's the same thing I have here in the Jupiter. It's the acceleration factor, which is pre-calculated. It's the GR thing times. So this case is dv, right? So it's the we are already we take the acceleration, right? This is a factor. This is a this is a thing they do in Live2D. So this is basically a gravity factor, right? So it's the factor times the acceleration, and then times the sine, ignoring this part, right? So this is the same thing as this. The d of the derivative of the velocity, which is acceleration, which is the double derivative of y, is minus some constant factor, whatever, times the sine of the angle. The same thing we have here, right?
Yeah.
And in this case, the factor is basically a gravity factor that you get to configure in Live2D, and the actual factor is the square of the original frame rate at which it was simulated in the first Live2D version.
Okay.
Basically, they were because they were doing this every frame, right? They basically didn't consider to make this frame rate independent. So when they simulated it at 30 FPS, it's like the number here goes away, basically.
Okay.
So basically, their gravity was 1, right? And then if you simulate that every frame, you get if every frame is 1 second, right? And then gravity is 1 meter per second squared. That's how they simulated it, basically. And because we have actual seconds here, not original frames, and because this is acceleration, which is squared, you take the original frame rate, which is 30, and square it, and that's actually how you adjust from there, based on frames original version to something that is based on real time. And so basically they don't have like a 9.8. They don't use physical units for any of this. It's just, they just kind of wing this.
Okay.
So that's how you do the Live2D version. I actually wrote, it's on my laptop, I haven't pushed it, but I have like a formal description of this with like LaTeX formulas and stuff.
LaTeX?
Yeah.
Kawaii.
I have a GitHub thing that I haven't pushed yet that has this explanation.
Okay.
So yeah, I would say that maybe what I have right now is pretty close. I think if I make it a tiny bit smaller, so maybe the damping factor is like 1.55. That's pretty close, actually. Starts a little big and then gets a little too small, then it kind of comes back. So now what I want to know is, okay, does this work for different conditions, right? Because otherwise I'm kind of wasting my time here.
Yeah.
So let's see. If we change the pendulum acceleration, so this is using a test file for the physics, which we can edit. So I'm going to do that. And this is here.
Minasan, I'm falling asleep.
You're falling asleep already?
What do you want me to do here? I mean, tell me what's my purpose. Just to figure everything out.
I mean, I'm trying to... I'm kind of getting to the point where it gets interesting.
Okay, I'll stay with you.
So the first pendulum here, right? It's just one. If I change the acceleration to like 0.2 and save and run this again. Okay, so now what happened here? Hold on. See, now it's totally off, right? Like, so this idea doesn't really work like that. What happened was that when the acceleration is higher, they lose a lot more, which makes sense because the acceleration is also applied kind of like in terms of you see the velocity is right? If I set this like 0.3 and run it again, the frequency is correct, but the damping factor is not correct, right? So we need some kind of correction for that.
Oh.
So we can try to fit something. We can try to fudge it. So let's see if we can maybe do that, right? If I do the see, that's the opposite, right? Now we are too low. So how about we set the acceleration to if you have 0.5 here, it kind of looks like maybe we can just multiply it by the acceleration. So maybe we can say damping factor is this, and then times the acceleration, and divided by 0.1, which is like the original factor we had. Okay, actually that works.
Yeah.
That's pretty close,
Yeah.
right? So it looks like if we make the damping factor vary based on the acceleration of the pendulum, that actually works pretty well. So now let's try like 0.2 here. Yeah, actually that's pretty close. Don't you think?
Yeah. I just think it was better before.
Hmm?
It was better before.
What? No, it's pretty close.
Okay.
What do you mean? It was better before.
Like the blue part didn't show like 10 minutes ago. Okay,
Huh?
fine. Never mind.
No, we were here at 0.1. This is the original version was here. What do you mean the original version didn't show? You mean this?
Yeah.
Yeah, it's good at this velocity, but like,
Oh, okay. You change the acceleration and it's a little different.
yeah, so it's still a little off because their simulation is not like, it's still imperfect, as you can see here, right?
Mm-hmm.
In fact, now they have some weirdness going on here. I mean, acceleration is very low. There's they have some strange like
This is
weirdness.
the cold
They have some weird hacks going on here. Did I turn that off? I don't know if I turned that off. I did have that off. Yeah, I actually don't remember why theirs starts smaller here. Actually, it's a little strange. But yeah, their simulation is just so broken. But like honestly, like I consider this good enough. Like you're not really gonna notice in a model that it's swinging a tiny bit more like that.
What's the green line?
Good question. Forgot what that is. I forgot what the green line is. The green line is the initial position, I think, of their pendulum, and I forget why that is different. We have the reference, we have the state, and then we have the arctan. Oh no, this is the initial angle. What is this? I forgot. Oh, I think this is like, yeah, it's like the initial angle of their pendulum. And I forget why I was doing that. I think that's because I was using that as a simulation. That's a different way of simulating it myself, and I didn't use it. So I forget why their initial angle is not exactly 1 here, though. I think it's probably because they already apply some gravity or something. How was I doing this on their pendulum? I was like stepping it a bunch of times. Oh, that's why I think. Yeah, it's because I'm there. My API doesn't have a way of setting the initial angle for their pendulum, so I just like simulated, like for 10,000 frames, and so it wasn't quite there. So now it's better. That's just an artifact of this silliness I have going on here. Yeah, so it's not bad. It gets pretty close. And if we do 0.1, it's like we're a little high, but it'll probably get closer later if you wait long enough, you know, if we make this like 45 seconds. That's kind of close. And if we do it the other way around and we say 5 seconds at acceleration 0.5. Yeah, I mean, it's basically, we slow down a little too fast when acceleration is low and a little too slow when it's high.
Right.
But not by a lot. Which makes me wonder if, actually, I should be putting the pendulum acceleration in here. In V times pendulum acceleration, because we have this correction factor, right? So maybe we should be putting that there. And if we do it like that. Okay, so now we are on the low side. Slow down too fast. And if we make this 5.
Well.
Now you always slow down too fast, so now I think we can correct for that. So if we change the factor again to correct for that. That's getting close. Okay, so now it's pretty close at low velocities. And then when we do that very fast.
Very fast.
Make this work 5. No, now we're still off. So now we are too, hold on, we are too, at low gravity values, we slow down too little. Was it better before? If I put it in the MC in there, 45. Yeah, it was kind of better before.
Meh.
So the damping is too high when this is big and too low when this is small, which means we actually want to do the opposite. Actually, it's like 1 divided by 1.1. Look, now it's a little closer. Yeah. And so if we do 45 here and we make this 0.005. That's pretty close now. Not perfect, but pretty close. Nah? And like, you're never gonna use a pendulum that is this slow in Live2D because look, it's like taking like a minute to even kind of slow down, right? So no one's gonna do that. And if we do something in between, yeah, it's close enough. I think we can use this kind of formula then.
Yeah.
Let's try 1.2 here. And if we do 1.005. Yeah, let's forget these things are wrong. Okay, this is too big at one. Yeah, so it's 9.5 actually. That's pretty close now for the slow version. And if we do the fast one, cycle 5. Yeah, that's pretty close. I think we can work with this. Nah? Like, no one's gonna notice the movement being this slightly different in Live2D, so...
No one's gonna know.
I think that's good. I think this is a reasonable enough, like, fudge factor.
Yeah.
And the point I'm trying to make here is that this is, like, it's not a very complicated formula, and I can simplify down some of these constants later, right? Now, there's more things we have to figure out, though. So, this is gonna take care of the loss in momentum over a unsteady state. But now we have another thing we have to figure out.
Yeah. What's the thing?
You okay?
Yeah.
He's like drawing. The pendulum moves, right?
Yeah.
And when it moves, Live2D does some fairly strange stuff.
What?
Because it basically, this is that kind of adjustment thing again, right? So if the pendulum moves somewhere else, I like move it here, right? If it moves here to the left,
yeah,
then what happens is the pendulum is originally actually it's originally here, right? In this position.
Yeah.
So what ends up happening is that this rod moves to internal snap, moves to the same angle as the pendulum, right? And then it snaps back like that. But if you look at how that's done in the simulation,
yeah,
what we end up having is the velocity is the is always the new position and minus the previous position, no matter what happens. And we are taking the position relative to the origin, applying all the things we've been doing, and then normalizing based on the new origin. Or actually, rather, we already have the new pivot, and we basically normalize, right? So what happens is basically we are doing all this math here where we originally were, which is like fine.
Yeah.
And then we snap it back here.
Yeah.
Okay? And this is a new position.
Yeah.
Now, what happens though is that now the angle at which this moved, right?
Yeah.
The delta motion of the pendulum is basically this, because the origin has been dragged, right? So it has done this motion, and then this becomes the new velocity vector for the next frame. So this kind of makes things quite confusing. Because if this were actually, if this pendulum were moving normally,
yeah,
the actual velocity vector would be different because we have this line here, right? This is the original angle, right? If this, sorry, it goes from the bottom. And snap it. You snap. So if this were the actual motion that happened, right?
Yeah.
Then the amount of the pendulum moved is like here, right? But that's not what happens. it's very confusing, kind of the way this drag motion is applied, right? It changes the like, how do I put this? Like, it's just very strange. It has this. It's very difficult to like simulate again, you know?
Okay, see.
So one thing I want to do then is, okay, we have this algorithm right here.
Yeah.
What happens if instead of simulating the pendulum being at a certain angle initially, if we simulate it with the origin moving at a certain point, right? And the first question is, how do we even do that in this kind of simulation system, right? Because we have this based on angular position, but then suddenly we are dragging the pendulum over, and you will notice that in the my physics lab, in the demos they have here, they have a movable pendulum. Where is this? They have this, which is kind of what we have, right? But the way they move the origin is always smoothly, right? By doing some kind of acceleration thing. We don't have that because we need to be able to move the origin like immediately to the new position, right? So how do we take a instantaneous change in the input position, which is based on like the Live2D parameters, right? And how do we convert that to something that is going to change the state of this physics system in a way that doesn't break everything?
Just start at like stable, because like teleport is not a physics thing. It's supposed to move very slowly from one point to another, right?
Yeah, but we are, you know, this is based on frames, right? So it's like we have a new position for the pendulum that has to be the new position on the next frame, but we don't know how we got there, right?
So just pretend they didn't go there.
But we have to, because it has to be updated to match the new position, right?
Just change the position of the origin.
Right. But we are simulating based on angle, so we need to convert the change in the origin position to a change in angle.
Okay.
Right? So I think the first thing I need to do here is introduce a change in position to their pendulum and then try to match it. Okay? So let's do that. Let's say if I equals n divided by 2, actually n divided by 4, let's see, a little closer to the beginning. Let's introduce a change to their chain. And move the x position. So you can see what happened here, right? At that point, we yanked the pendulum over, right? And so it started swinging again. We need to be able to simulate this. Let's do it a little earlier, actually, so we can see the change when it's closer to like, yeah, like I want to have a little momentum here, right? And we're gonna try multiple places for this. So what they are basically doing, assuming the pendulum is not moving, right? If you just drag it like this when it's not moving,
yeah.
What happens is that it clamps down to the new position here, and then that becomes its new momentum, right? If it is already moving, you're basically adding to the existing momentum. So let's see if we can do the formula for when it is not moving, and then see how we have to adjust the momentum, right? So at this point we say, okay, when this happens, the input x is 1. We want to do the same thing for our system. Now our system here is described by this array of values here, and the only ones that matter right now is the I already wrote some of these here for the experiment. Okay. So we have the initial angle and the velocity are the only ones that we're using so far, the y and v, right? This is for the for other stuff we're gonna add later, maybe. So if we modify the angle, we need to basically calculate the the new angle relative to the new position, right?
Mm.
So first we calculate the current position. Which would be the state. The 0 is the angle, right? This is called y here. And the essentially what we're doing is, okay, we are changing the pivot point. So the delta x in this case is 1. And we want to calculate the basically calculate the vector of the position which would be the sine and cosine. I'll do NP array.
NumPy.
So I turned it into a NumPy array, so it's... The x position would be the sine of the angle. The y position is the cosine of the angle. And then times the length. So this is the pendulum dot... What is that called? I have the length in here. It's called radius. Okay. And then because we are changing the new position, right? We would take the x coordinate is the only one that is changing in this case. We'll worry about rotations later once we have that. And then we want to take the arctangent of that, and that's the new angle.
One.
And I probably did something wrong here, but let's see what happens. So if we take that as the new angle, and the y is STI is the current one. And I'm actually going to do it here in cur. So I want to not modify the current position, but actually make this a change in the current data.
Yeah.
So how do I think this is gonna this is gonna extract. So we say cur 0 is the new y2, and the velocity, the angular velocity needs to change by the basically how much the angle changed times the delta time, because in this case this is like instantaneous, right? So we're basically saying, okay, the change in position times the what's the FPS that I'm using here for this simulation. This is just, do I have a DT in here? I think I have a DT in here somewhere. H is the delta time. Okay, that's not working. Where's radius? Okay, so I have it backwards. It's in the wrong direction. Okay, actually, that's pretty close. That's not too bad, right? We're a little off, and then it trails down faster. But that's not too bad. That's like, you know, it's reasonably doing what we want.
Yeah. I don't know what I'm doing.
You don't know what you're doing.
Professor, I'm lost. Would you let me Run away from the class.
What do you mean you're lost?
What do you need me for?
Oh, you draw beautiful things while I'm explaining, so... you need to post this. This is so good. Oh my gosh, you have no idea. She just drew this on the back like a McDonald's delivery paper. Ah, amazing. What happened there? Ah, yeah, so there's jumps, like... You can start to see the frames there, but... What?
I misspelled angle to angel. I think I'm really asleep.
Let's increase the frame rate a little bit and see what happens. Oh, that's interesting, actually. If we don't do this... Wait, why is mine frame rate dependent now?
Bamba.
Hold on, 120. Oh, because I need to also emulate like their change. Yeah, okay, it's because like theirs is frame rate dependent, so mine has to be also. Hold on, no, does that make sense? No, oh, it's because yeah, okay, so I need to like yeah, like if I run theirs at a slower frame rate and then mine at a faster frame rate, it doesn't do what I want. I need to like, if I do that, so it's like 200 FPS. Yeah, it still matches pretty well. And then enable this jump thing here. Yeah, so we're still a little off. Looks like they gain more velocity from the jump than we do here. What happens if I make the jump in the other side? If right now we lost momentum, right? The actual delta is the same. You can see that the jump here is basically the same as theirs. But they gained a lot more velocity. We did not do that. So if I change the... Let's see what I'm doing here. If I do it in the other direction, so if we do this instead of when it's... Yeah, like in the other is much closer. I see, and in the other direction, look. It's the other way around, right? This is not doing what I want. Oh, it's just divided by age. Okay, that's too much. I think this makes a lot of sense. That's funny. It's like it went around the whole loop. What's going on here? Like, what is this kind of factor they have for how much that it gains in velocity? It's almost like it's 30. Oh, that looks really sus. That's kind of close. Is that consistent? No, it's not. Oh, actually, that's... Hold on, so it's like it's... I got the plus and minus backwards? Ah, this is a little strange. So I am subtracting the... hold on. Yeah, this isn't working. So this is in the other direction, right? And so what happened is, okay, the pendulum was, in this case, it is moving from the edge down. And so we are here, right? It's being dragged in the other direction. Right, but the momentum does not change quite based on the... Yeah, it's because they okay. See, this is why this is so confusing. You kind of have to see it to understand it, right? Let's copy and paste some of this. So in this case, the pendulum is falling down, right? And it's coming back from one side. Make it a little more exaggerated. And then the X position gets changed, right? It gets changed to move towards the left. So now we are like here, and it is going back to from 0.50 to about point. It's going about exactly the other way around, right? So it's angle-wise pretty somewhere around here, right? So really, we are approximately flipping it, right? We're doing something like this. So the bob is moving. Sorry, the pivot is moved from here to here, right?
Where?
And I can put the marker on. Okay. So the pendulum had some momentum originally in this direction. Originally had something like this, right? And now that we dragged it over, it loses its momentum, right? So my simulation here, you can see that what happened is that it continued with the same momentum it already had, right? Which is actually the opposite of this curve because it pretty much just instantaneously jumped to the other side. But what they did is, okay, the momentum mostly died away because of this jump, because it was moving in this direction, so it just gets lost, right? So I think what we need to do is we need to actually do the calculation on the momentum like this too. And then apply the same change. So we say dpos, and then this is the dy equals curve 1. So this is actually it's not the pause. It's more like the pause 2, right? We calculate a position. We calculate a second position based on the dy we have, right? The current momentum. But that has to be multiplied by like the frame rate, because we have the this is an instantaneous jump.
Yeah.
Does that make sense? No. I'm trying to rotate the vector basically, so it should it matter what it is? Maybe not. Oh, I think I know what I can do. Basically, the if I take the vector as like the angular velocity is being multiplied by the difference in the angles, which is the how do you say that? It's like the dot product. Ah! 難しいこれ。
そうです。私はそう思います。
Yeah, okay. I think you basically take the difference in angles, dy equals y2 minus y, and you take the cosine of that. Is that gonna do anything? That actually just messed everything up. What? How? Oh, I deleted the curve. Hold on. Ah! See, now that makes sense. Wow. Now that makes a lot of sense.
Wow.
Does this actually do the right thing? Hey, that's pretty close.
Hey.
Okay, so this works. So basically, you take the cosine of the change in angle, multiply the current velocity by that, and that's exactly what we want. Yeah, that's pretty close. Not perfect, but pretty close. And actually, the only difference here is that we are doing the jump earlier, so they have like a lag of 1 frame. So I think we can probably just honestly, I think we have a lag of 1 frame the entire thing. So I think if I just move everything to the left a little bit, it will work. If I just do like a 1 step of theirs first. That's the other way around. Okay, so if we do this the other way around like this. No, now I'm ahead. Hold on.
Mwah.
I think I just want to do this after. So if we put the input X in here, and then just change it, 2 equals change input X minus 1. And I need like an st. Okay, just do the dx equals st I 2, and then we say cur 2 minus st2. You can just say okay, now this is backwards. And we don't do this arctan anymore. Actually, I can just plot the st2. This is the x position. And then what's the if we put it here? No, I'm doing curve 1. Huh?
Bye-bye.
Why is this not updating now? What am I doing wrong? Why is that not pretty? Huh?
なんでどうして
Are never there? Hold on, if dx... Why is dx never 0? Curve 2 minus sti 2. Huh? Is it because this is like mutating in place? Okay, yeah, something like that. But I'm still early on the change. SDI. No, that did not work. Okay, that's closer. But now the now it's actually worse. I was gonna undo because like whatever I'm doing here is not helping. I think that was a bad test what I had there because it wasn't really in a place where the DY was getting updated, right? Yeah, okay. I think this is close enough. So if we do this at 60 FPS, yeah, I mean that's pretty much what you get, right? I think this is close enough.
Yeah.
Hold on, what am I doing here? DXT and FX and yeah, okay. Oh, I can just do this. And then I can just do this at the bottom and it'll make it faster for theirs. No? Whoa. What just happened?
What just happened?
I need a, equals change the input X. Okay, yeah, like that. Okay, yeah, now it's a little closer. But it doesn't help if I do it like that. Yeah, this is still closer anyway, so... I think we're just gonna go with this. Okay, so this looks like a reasonable adjustment for moving the position. I mean, depends on what you're doing. It's not going to be exact because, you know, the simulation is a little different. But this is for like a huge change in one frame, right? For small changes, it would be much closer. Like this, right? You okay? Sign is like sleeping.
Hi.
Do you want to take a nap?
Hi.
You need to post this. Oh my gosh. Can you take a photo and we put it on the screen?
I'm really bad at taking photos of this.
Why are you really
like
bad at
shadow
taking
and
photos?
stuff.
What do you mean shadow? What?
It has my color on it.
Your what?
Color. Hey, the glass has reflection.
Fine. I'm gonna
Oh god.
drop it on.
I cannot. At least put it in the center.我们呢，先生？10 I fall asleep. 大丈夫? This blanket is so warm.
She's like falling asleep.
I'll see you tomorrow. Thanks, guys.
At least let me show them what you just drew.
You hear the sound of shaking the markers. I haven't opened all of them.
Let me put this in here. Let's see.
Please don't post my reflections.
I'm not gonna post your reflections.
Hey, you look like you're about to sleep. I did. I had some dream about Ragtang. Ragtakuta.
It's so cute. Oh my gosh, let me show you what she just drew.
So dark.
I can fix it.
I gotta fix it. I gotta fix everything. That's scary. You fix everything. You're a fixer.
I don't have that. Okay.
You can just use OBS.
I guess.
I'm an OBS master. I mean, I don't come into OBS unlike you.
Use this though.
Yeah, increase the contrast.
There. That's
Yeah, no, good.
okay.
Maybe saturation. You have saturation. Good enough. Yeah, good enough. Like, where are you gonna put it?
Hmm?
Where are you gonna put it?
On the screen.
On screen. On screen where? To replace me? God. Just Control C. Please don't paste my selfie. Oh god. I put a random Japanese character there because it looks cool.
There you go.
Okay. Are you happy?
That's so cute. How are you so good at this?
I'm not. I'm just good at not concentrating in class. That's what I do.
Yeah, on paper, like on the back of a McDonald's delivery thing.
They put a paper under the delivery
Uh-huh.
to prevent food getting stained. They do that in Japan.
Yeah.
I hope you enjoy it. I'm gonna head out and buy some grocery.
Okay.
Is that okay? Little
okay.
fingers so cute. Sorry, I didn't count them. I feel like an AI because I can't draw fingers straight. Alright, I'm gonna go out. You need food because I'm hungry.
She does do digital art too, yeah.
I left Chikawa なんだっけ焼き takoyaki. You would like some?
I might want some, yeah.
Okay. I'm gonna.
It's not the fat absorption paper. This is the paper. Okay, when they deliver and they leave, that you can choose to leave your food outside the door. Okay. When they do that, they put a little sheet of paper under the delivery package, so the delivery package is not touching the floor. It's a very Japan thing to do. You know, because the floor outside is dirty, so they put a little tiny sheet of paper and then they put your package, your big brown McDonald's delivery package on top.
Yeah.
And that's the little paper on the bottom. Is it just like an A4?
I used the A1.
Huh?
Because I used a quarter of the A4, so I used the A1.
No, that's the other way around. A6.
Okay.
A6.
Alright. So what would you like for lunch? Something, anything?
I don't know. Something.
Frozen food? Frozen healthy food?
Yeah, that'd be nice actually.
Okay.
Mm.
I might.
Here, drink the water.
Yeah, I might take a nap first.
Okay.
Your stream is very good for resting. Alright. Ciao.
Hi. Bye bye.
Isn't ciao hello? Adios.
Ciao is like, I think it's both. I don't know. Anyway,
Ciao.
it's like bye, but yeah. Anyway, okay, so this kind of works. Maybe close enough. Maybe good enough for now. Let's see how people react to this kind of like physics thing. So, So this is one way to do it. The other way to do it is to essentially have this be applied as kind of an impulse on the pendulum. I mean, that's kind of what we did with the velocity. So maybe that's okay. So let's try doing this a different way so we can fit it into the derivative equation directly. Essentially the same thing would be saying let's use curve 2 for dx. So we have like the delta x as curve 2. It is this one here, right? So we set everything to 0 here because this is like old. Actually, how do they do this movable pendulum stuff? The way they do it is they will have the anchor block. Yeah, they just apply like the motion in there, right? So I think if we just do let me turn the peak off. I think if we just I think think if we just do like... Basically have it as an input to the deriv function, so it doesn't really need to be part of the curve values. Now I don't know if this should be used in all of the iterations of this thing though. That's a good question. How are they applying this in this motion, I wonder? Yeah, maybe if this is in the deriv function, it actually will work better. So let's try putting it in there. So if we put it in the deriv function, we're basically applying this as a derivative. And so what we are changing essentially is the so we have y and we call it v for dy. So we say this is probably not gonna work properly, but we're gonna try it. So we do need the time step to calculate that. So if we consider it an impulse for one time step, we would say dy plus equals it would be y2 minus y divided by h, which is the time step. So that's how much we apply to the velocity change, and then the position change would be like instantaneously changing by the delta divided by h. So it's gonna get multiplied after anyway, and then dv is actually, since we're multiplying the original v times times a factor, the dv would be how much we want the velocity to instantaneously change. V times the cosine, and it's negative, and then all this divided by h. I think it's gonna be ridiculous. Okay, it's not ridiculous. It looks like it went. What happened there? Why is theirs different now? Okay, so now we have this. That's actually wrong now. Yeah, that's definitely not doing what I want. Even the position is not moving how I wanted to. And that's probably because of this algorithm there, right? Hold on, why am I editing this? I false. I'm being silly here. X and 0. Y2 minus y divided by h. Yeah, there's some kind of factor going on here. Yes, it's from like minus 0.90, which is this one here, goes to 0.33. So it's supposed to be here, but it is actually, because of this operation here, it's actually like rounding it out. Why is it doing that? Yeah, it's only changing to 0.066. If we do this, it's gonna go crazy, right? So yeah. Yeah, I think this doesn't really work very well for the like impulses like this. Okay. I think that's probably because the Hold on. How does this work? That's a little closer. Okay, that's kind of close now. If I do this, it's probably not gonna be that good. Yeah, it's too much. It might be this because we are. Was it divided by 3? No. And then the other factor here, the dv. Yeah, that's getting kind of there. I don't know if that's accurate, but let's try some other positions. No, that is not very wrong. What happened there actually? Is that even right? I do the instantaneous one? Yeah, okay, so this is the instantaneous one, and for... Oh, okay, it is. This one's also off for this one. Why? What's going on now? Something's wrong. Huh? This is really strange. So this algorithm works for this case. Oh, I think it works only on the lower side. So I have a I have a... Like, I have a sign problem somewhere here. Should do anything as cosine. Okay, I'm gonna take a breaking bear back, but like I think something is wrong with my formula because like it only works on the negatives and not the positives. Unless I mess up the Live2D version. Be right back. I'm back. I forgot to. This was good. Water, I think. I don't know. Anyway, so I think first of all, does this work the other way around? Because if I flip the angle, it's much closer, and if I flip the initial angle, yeah, it's still broken. Okay, so clearly I have something wrong. Does this make sense? So this is moving past the center point, and we drag it to the left. And so there speeds up a lot. Actually, let's start with the initial angle that is small. Yeah, so then it works fine. Yeah, so when the initial angle is higher is when this starts to break. So this means it's looping around, right? This is going around in circles. Why? It could be a bug in my implementation of their algorithm. Whoa, what happened there? That's not right. So we're let's put this print here. did I do this in theirs? Because I'm not sure if I ever actually simulated this amount of craziness. No, it just that subtracts the position, then adds it, right? And then takes momentum. Like it's just totally implicit. Wait, this is that point. This is that point where the motion is so big that it becomes very dependent on the initial angle. Because the X position motion is actually yeah, when the pendulum is close to 90 degrees, it's very becomes very unstable to large X motions. Yeah, okay, so it's just like because we moved a little higher, theirs is less than 90 degrees, so it actually cancels out. Ours is greater than 90 degrees, so it actually goes all the way up. Yeah, this is just like yeah, anytime this goes close-ish to like minus 1 point something, it's gonna be wrong. So that's kind of expected. Okay, so go back to let's make the initial angle smaller, so now we're much closer, yeah. And what was the case where this was breaking? This one. Okay, so this one's a little less explainable because it's -1, which is not too close to 90 degrees. So what's going on here? Yeah, this is the position when the anchor is moved, so the velocity doesn't go up that much because the spring is. There's no spring is the thing. This is a pendulum, so it's a rigid pendulum. And okay, so what's the case that's going on here? What we have is from 0.24 to 90, the actual motion is fine, but then the velocity is very different. This is angle. What I'm plotting here is angle. Okay, let me look at there. So the velocity is based on new pause minus self pause, and that has the pivot added. So they're using the velocity in like absolute coordinates. So what happened here is I want to somehow, I guess, plot this motion here. So the actual velocity update here, if we do the arctan of y and y2, says y, y2. Now? There's that. Thank you, that's amazing. So okay, they're using this implicit derivative stuff, right? So, when the bob moves like this, then it gets normalized, and but that is relative to the new position, right? So if we have the new position, which is here, and then add like the new angle. The new angle, and then we use this as minus dx, and so the delta is that. And so then if I take the arctan, we take delta equals pos 3 minus pos. And then if I take the yeah, if I take the arctan of that, is that what I want? No, it's moving. I want to get this relative to no, that doesn't make sense. This is so confusing. Yeah, it needs to transfer like momentum to the bob. I'm trying to figure out how this is like the way the other one is doing is that it is calculating everything in terms of velocity in like a Cartesian system. And so what I want to do is I know how this the angle change is fine. The y2 here is fine, right? And the new position relative to the original one is actually this plus the x. And so then the delta is how much it moved. That's how it is calculating velocity. But I mean, to take that relative to the new angle of the pendulum, and then the actual change is Vy times the cosine of is the absolute, which I did in NumPy. The normalized thing. Yes, the norm. So I think I had to add that change factor in there somehow. I try to have a lot of like signs that are wrong here. This is so confusing. Why is it so close sometimes and so off other times? Nah, this doesn't make any sense. Let me rewrite this. Pause before equals y times, and let's actually put the original dx in here. Does negative make sense? I guess it's just because the angle is the other way around. I can use this sim.normalize thing. Let's actually print this out like this. Now, pause before, pause after. Let's put this print. Do the signs like that, as before. My pivot. Pivot now. That doesn't look right. X before, X after should be a different response after. Is normalized. Oh, hold on. Y after should be, without the pivot. No, hold on, what? Okay, yeah, like that. So, X before, X after. Oh yeah, I need to not do this. Yeah, so that doesn't do that. So it's this pivot center before plus 4. Yeah, okay, so that does the right thing there. Yeah, okay, so that's fine. And now let's see what happens with the funny value. So we have that. So now let's start doing the like the velocities. D pause equals pause after minus pause before. So for the velocity, we can say d pause. This is v. Sorry, this is vv before. Would be the dy, and it would be times the angle at 90 degrees. I think that's how you do the rotation, like that. And then XD after. So v before would be dy times xd before. That's the vector in the velocity vector before the change. VV after is VV before, VV after. These are the motion vectors according to the current calculation I'm doing. And then we have the change in position. No, something's wrong here. V for D, X, D before. Oh, because this is an array. I really should plot these somehow. And it should be multiplied by the h, I guess. Well, this is per second, so whatever. Wait, this position after doesn't make sense. Hold on, what? I need to start plotting these things. How do I do matplotlib like XY plots? There has to be a way of doing this. Science is there forever. Hi. Let's see if I can make some sense of this stuff. I really need to draw it somehow. The vectors. Let's do something easy for vectors, right? Okay, yeah, like this. Oh, quiver. That's how you do it. Okay, good. Why is this 3D? I'm confused. Why is this 3-dimensional? Maybe a side by side would be nice. Except now it's too high. Okay, hold on. I mean, I guess it jumps to the top, so that's nice. Oh, because these are the that might have the okay, yeah, for 2 arrays. Okay, I can just do it manually, I guess. Vector origin delta. It's from 2 actually. Scale is weird here. Okay, now that I don't want to scale the arrows, but I want the plot to have a reasonable dimension. How do I do that? Access bounds. Okay, and now the vector is wrong. Okay, I guess maybe not a quiver. Maybe I want a just a line. Which I guess would just be plot. Do we need that scale units thing? Ah, okay, there you go. That's what I wanted. Okay, so these are gonna show the vectors properly. Okay, so let's see if this makes any sense. Okay, so we go from P54 and pause before to pivot now and pause after. Why is this not scaling? Whatever, that's fine. And the Y is backwards. I'm gonna invert everything to make sense. Can I change the bounds to be the other way around? Yeah, that's nice, because Y goes up downwards in Live2D, and that's how this is getting calculated. Okay, so it starts out at yeah, so what's going on with the pause after there? Starts out there, moves there. What's going on? That's already backwards. So the position after is that I keep doing this up. This relative thing is messing with my brain. Position before is AX before plus pivot before. Okay, hold on. Oh wait, these are deltas, not positions. Okay, yeah, that's what I want. Okay, that makes more sense. Okay, and now this is backwards, which means I was doing this wrong. Okay, yes, I had the X wrong. It is not negative, I was just doing it wrong. Okay. Yeah, okay, so in this case the angle barely changed because it just moved to the left. And now I want to show the quivers. This is called a quiver, and then not set any of the scale stuff. Okay, that's the wrong X. Okay. Okay, that looks right. So that's the original velocity vector there. How do I make these like smaller or something? Okay, yeah, something like that. Can I make the page wider? That'd be nice. Full width notebook. There we go. Much nicer. Okay. Okay, so that's obviously not right. Hold on. So if we disable the factor, it has too much velocity. Can you make the exchange a little bigger so it's not overlapping exactly? Yeah, it's more like it. So the cosine thing, the factors, dy fac. Oh, and also I think these arrows are not getting scaled properly because I think we need to all print the, plot them all at the same time. So to do that, I think I need a Okay, like that. Yeah. So you can see how the velocity is smaller because the dy fac. Let me print that here. Is 0.34, so that is like 1/3 of that. And so that is correct for this case. So now what happens when we have one of the cases where it doesn't work? Alright, I need to set the width a little smaller, I guess. Yeah, that works. So what's going on with the vector here? This one, why is that going in the wrong direction? I think I may just set this a fixed scale. Yeah, okay, now the calculations are wrong. So the xt before, okay, yeah, so the y is not supposed to be inverted on this one. No, that's not right. Huh? And just stop doing this silly vector rotation stuff. I have a rotation function. Why am I not using it? That doesn't look right. Oh, it's because the scales here are not actually equal for x and y. How do I make it do that? You did set aspect equal. Ah, that's more like it. Okay, there we go. Okay, so that's the first vector. The second vector you can barely see. Let's change the color there. Let's not print this green one. Okay, and now let's make them a little bigger. Okay, that makes sense. And now this one at the top there doesn't make any sense. So the way the original thing is calculating the velocity is the absolute position So it is applying the velocity on top of that. Right, so when the velocity is this is correct, and then it applies the little tiny existing velocity on top of that. So it would be something like no. That did not work. Oh, right. I need to like scale the quiver scale or something like that. Yeah, so you get that, right? It does that vector to the back, and then it adds the original vector, and then it projects it back into that blue line. So that is essentially what it's doing. And I think that is different to what I'm calculating. So that's probably when it goes wrong. So I need to project that point to the perpendicular to the line. Now that doesn't make sense because it is actually adding the... Hold on. Since this is actually happening per time step and we have the wrong time steps here, this is a little confusing. Let's set the scale to 160 and the time step also to 160. And we can make the thing a little slower. Okay, so this is pretty close. Yeah, okay, I think one of the problems is when the time step is really small, it's really hard to see here what's going on. Okay, so here's monkeys, but it's a little different. I visualize this and it makes sense. I'm gonna take a quick break. Be right back. Okay, I'm back. I'm gonna eat some food and then I'm gonna probably do some more drawing to make sense of this. Because I think what's going on is that, at least at... because the original implementation is based on taking the derivative of the position. So it's taking into account the time step, right? Now here, the time step is fairly small, so if you actually just draw the quivers for one time step, they're very small. But then it shouldn't be that off, so something else is wrong. Okay, so maybe I can do it like this. Maybe I can figure out what the bug is. I'm going to eat a little bit and then come back. Yeah, this is the second stream with a new model. Okay, so let's try to figure out how the velocity is affected here. So essentially what this is doing is it's taking the change in position, but it also added the original motion, right? This vector here for the frame. So we can't really print that addition. We can't really show it on the graph because of the scaling issue, but we can try to do the calculation and just show the result. So I think what it's doing is, okay, it takes the position difference, and it also adds the original velocity. So if we print from pause before to pause before plus depause. What's the orange thing? Yeah, okay. Oh, I can show the quivers at 1-1 now, actually. So that's nice. Yeah, okay, so this is the original velocity vector. This is the same one applied to the new position, and then the actual velocity vector you end up with is this orange arrow here. And so then if you project that down to oh, but the problem is that these are in so it's supposed to be in frames, right? So this is per second, but that's not right. We have the position change, but this is actually more like a 1/60th of this. This doesn't make sense. But the so the change in one frame would be position after minus position before, plus the velocity before. So it's actually these divided by h plus VV before. And so then what's going on is that velocity gets essentially clamped back down. That doesn't make sense. Ah, what's going on here? It's not print that orange one, which doesn't make a lot of sense. Yeah, so the delta position in one frame later is going to be the change in position plus VV before divided by H. No, times H. So that's going to be the one frame difference. So that's what it's going to apply to the pendulum later. And so then what it's doing is, gosh, this is so confusing. Yeah, it applies that delta. Okay, let's so that's a quiver, so I'm not confused. In position after, and this is the VD pause. Yeah, you get mostly going up like that. And so then this is all this is multiplied by 8. So this is the actual per frame velocity. And so then we want to normalize that precision out plus VD pause. And then yes. So subtract the pivot, normalize it, add it to the pivot. We have the later position. Okay, there we go. So now that is like the one frame later position, the orange one, right? And from that we get the actual velocity that it's going to compute. And we divide by h. So let's call this v later. Okay. So now we run a pivot position after in this v later and make this orange. Okay, now we're still very far off. Yes. Okay, so that's the original change there. In velocity in red. I'm gonna change the scale. So yeah, it speeds up a lot, and that might explain this. So what happens if I set that as the velocity now? If I take the angular the velocity there, and I think it's essentially it's small enough I can just take the absolute value. So I want the norm of that. The norm? Yes, the norm. And I need to multiply this by the angle. Nah, I should actually rotate it. I can just take the arctangent. Y later equals arctan2 x later. And then just say curve 1 equals y after divide times h. Let's call this v2. I don't even know what variable names to use anymore. This is so confusing. So we have VV before, VV after, and the dy fac. That doesn't look right. Divided by h, not times h. That's not right. Something's wrong with the angles here. Why is this negative? The angle was increasing when it... Oh, hold on. These vectors must be backwards. Hold on. The angle was... It was still going up. So this vector is backwards. That doesn't make any sense. That vector is backwards. So AXT before is this is minus pi over 2. Okay, there you go. So that's the way that vector is supposed to go. And so then the after is also inverted here. This is has the Is that right? No. I'm bad at vector math. Okay, so swap and invert y. So like that. Okay, there you go. So the red is the original, the blue is when that is projected down. I need to sprint the velocities here. Yeah, so you get a crazy velocity after that. Negative for both. That's where you get the weird thing going back. Because we are storing the velocity as relative to the dt. So this is the real velocity. And so if we calculate the same thing here, it would be d pos divided by h. Yeah, it's roughly the same thing you get here, right? And so then VD pos divided by H is probably the same thing as they have. It's not, but it's somewhat close. And we didn't apply gravity yet, which is part of the problem. So I guess let's add gravity to here. hold on. So it's what it's doing is it's oh gosh. I literally just copy and paste that code in here and see if I can make sense of it. I'm just gonna copy and paste this mess of the code. So we have the so we have the pause before, that should be correct. So this is pivot now, there's the rel pause. And it actually gets normalized after, so that's the confusion, right? So we have the momentum. So the velocity, we can probably use the previous velocity, which would be axt before times dt times mobility. Yeah, so this is dy times axt before. So we're ignoring the input angle for now. This is just g. And then it normalizes. Let's put this down here. So we have So I'm not getting the same number. But it's pretty close. That's pretty close. The original velocity was not exactly the same, so that's fine. Okay, so now we have the written script in Python has a physics system, cubism, statistic physics engines for comparing the error. I have my own implementation of the cubism algorithm, and I know this is essentially correct, like to within floating point position. And I'm trying to make a new algorithm for physics that is better behaved, but still roughly has the same properties. And so I'm trying to get the instantaneous X position change behavior to kind of match. Okay, so if we do that, what happened there? I guess that already has new pause added. Yeah, I guess that's a new position. And so now with this velocity, we have to go back and reapply and renormalize. So that's the pause later stuff we have here. Yeah, there we go. Okay, that makes sense. So the original velocity was going in this direction, and now we have this new velocity that's going this way. And so if I set the if I calculate the angular velocity of that, so y later is arctan 2 of ax later. And now we're still wrong. I didn't set it. Hold on. Sorry, this is YV later. Okay, yeah. So this is going in the other direction, which is what I want. And then if I set the current velocity to that... what? I didn't update the angle. I guess I didn't update the angle, yeah. Current 0 is y after. Okay, yeah, now it's kind of close. And so then, Somehow we're still slow, even though this is actually stepping the velocity even faster. I'm gonna add another step here just to show what's happening after that. That's actually a pretty big number, so we still have something off here. Mm. So P after is the same as new pause, pretty much. Which makes sense because it's the same algorithm. the velocity later is there. So there's something different here. This number is getting normalized very differently after the second. Is it just because of the error of that? I mean, it's because it's adding gravity and stuff after that, but yes, if you add gravity, you start getting something close. Yeah, and then it's really close. Right, because we're trying to normalize the velocity after all. Gosh, this is so complicated. So now it's the simulation is closed, but obviously I don't want to do this crazy stuff. So is there some way I can simplify this and make it make sense? Okay, let's try out another few inputs, make sure this makes sense. Yeah, that looks fine. That looks close enough. Yeah. And also, I'm not supposed to be doing this here, so... Yeah. There's like a latency issue, but... I do next x like that and say cur x equals next x at the end. Where's last exit? Ah, there we go. Yeah. So if you delay it by like 1 frame, it's pretty much doing the right thing. I need to like not plot that. Figure it out later. So okay. The issue is basically that like this implementation is doing a lot of crazy stuff, and it all depends on the exact order of operations. So I want to figure out some way to avoid this mess. So what we have is let's set an angle that is a little nicer. Which is the one we had before that was very different. Let's do dy1, which is the intended dy. Okay, I'm gonna take a break right back. I'm back. Was I muted? I feel like I forgot to mute myself. So, okay, what's going on here? This has to, there has to be some kind of simplified way to do this. So, if, hold on. I'm gonna set the, I'm gonna do this thing here. So this is the old math. It's still pretty good in this case, but not in every case. So it's not a case where it is particularly bad. Here's one that is kind of bad. And so if I don't set that, now it's still bad. What? How is it this bad now? Oh, is this one of those where the angle is like just no? No, it's not. Now mine's an overestimate of the velocity in this case. Okay, it's a lot off, but it's not that far off. How does it end up this bad? So you have minus 17 and end up with like 14 now. Why? So it didn't work. That's what I expected. So now the other algorithm is much better. What? How? Okay, so is it just the velocity or is it something else? If it's just the velocity to like the -14 that the other one has. It's closer. It's actually closer to -10. Then how do we know there's 14 here? Why does it do that? I mean, this is gravity to deal with, but okay, so if I don't apply gravity here, I get -5. I have to think of this in terms of geometry because, like... If I make the X movement very small, and that is like wildly off now. Oh, sorry, because I did that. Okay, now that's pretty good. And with the other algorithm, it's still pretty good. Okay, so that doesn't really change much. Yeah, because we're at the top, so the velocity changes very little. So when it's a very small change of velocity, it doesn't really do much. So we need to test the case where the pendulum is closer to the center, which is where the velocity is largest. And now make a big change to X. Yes, these are all pretty close. Uh, okay, so this is one that it's closer to with the second algorithm. I'm just gonna go back to the one that didn't make sense. It's gonna undo. Hold on. Huh? Yeah, this is the moment it was really wrong. So this, when it was pretty much exactly at the tip there, and it pushes it forward. Let me see if I can just confirm this. And Yeah. Yes, it's much closer a little before. And it's pretty bad there. And it starts getting closer as it goes down. Okay, so why is it so wrong here? Is it because the initial conditions are different, or is it because of something else? If I look at the so the velocity is pretty close in terms of absolute like value, but then the what it calculates is pretty different. Let's add another step in here. Let me also print the point before, because maybe this is the position is getting messed up. Point before is what is this? P before. Minus 0.3 and 0.47. Yeah, that's fine. The position is fine. And then, so the problem is the velocity is wrong? I'm setting it to like minus 0.9 and somehow it's going crazy? That doesn't make a lot of sense. Oh, hold on. Wow. This doesn't make... oh my gosh, I am dumb. Yeah, this is the old algorithm. And with this one, it is undershooting by a lot. And with the new algorithm, it is overshooting by a lot. So why though? Because the cubism one is not somehow has an actual larger velocity, but then it somehow doesn't actually let's bring the angle here too. This one 6.3 is the angle, right? And yeah, the angle starts at 1.09 and then you get 0.736 and here you get 0.686, so it's actually going a little faster, which is right. But then how do we end up overshooting? That doesn't make sense. Let me print this a little wider. Wait, what? Oh, hold on. Why do I have cycle twice here? It doesn't make sense. Okay, yeah, so this is really off. Let's actually zoom in here. Let's make it 1. I think we're kind of running into the simulation like quantum problem here. But I need to not do this though, because this is gonna break it. I guess actually it's pretty close when I don't do that silly thing. But then somehow it goes way off. Why? So that means that I'm actually calculating the velocity pretty close. But then somehow... I guess I should plot the velocities too. I need like a secondary axis for this. No, that's what I want. Okay, let's try that. What did I do? Did I miss something here? I accidentally deleted a plot? Oh yeah, I did. This is 2. And then let's see if I can just get the... Instead of taking the norm there, I want to take the... I guess I can just multiply by the copy sign. Yeah, it works. And let's see if I can change the colors to something original. This is red, and this would be like cyan or something. Okay. So these are the angles, and that's where it messes up. And so the velocity is fine in the beginning. Then, okay, that's the jump because of the crazy thing that their algorithm does. And it comes back. It comes back, and we are somehow... You have a very different velocity. Let's do a little more width. Okay. Okay, this is weird. Why is this velocity like... Huh? I feel like this is my fudge factor getting something wrong. I think that's it. I think the problem is actually I'm confusing myself. This is just adding a big velocity, and the problem is that my fudge factor just doesn't work at big angles. What? Yeah, this is the copy sign should be copying the sign of the... yeah, it inverts for the... Yeah, okay, hold on. I need to do this a little smarter. How do I do this? I'll just do the same thing I did before. I'm sure there are better ways of doing this, but I'm like... I'm just just gonna edit the simulation file and have like a angular velocity thing. And I need to like restart the kernel for this to work. So then I do angular velocity. That does not work. That's not working. What did I do wrong here? Oh, I guess this is divided by dt. Okay, so in this case, we're already kind of far off before even the change. So, the fudge factor really is not great for larger angles. Okay, what happened here? This is a really weird one. This is not the damping anymore. This is like off. Using the second algorithm. If I use the first one, it's actually better, but not great. So what's wrong with the new algorithm? This is totally off. Like, completely in the wrong direction. Huh? What? This does not make any sense. I might just give up on this because it's ridiculous. I'm just gonna first cheat and put in the exact values from the simulator. Okay, so we have okay, now these are really close. The velocity here, minus 53.71, minus 32386, and minus 25.269, minus 25.237. Okay, those are really close. So that calculation is accurate. How am I getting this V later? That's different. Okay, that's better. So the G calculation is off. So what is it doing with the new position? The new position is should be about the same, hopefully. So the B before is minus 0.29 and 414. Yeah, new post is about the same, and then so then we have this rel pause. So it should be about the same, unless I missed something up here. Position later. Let's print pause later. So we have minus 0.324 and 482. Yeah, it's very different. So I have something that has to be wrong here. If I turn off the gravity, I can't because it is like that. I can turn off. Yeah, I can turn off the gravity by turning off ACC. For one step, we turn off gravity. Okay, what's going on with the x? The x dimension here is not right. The position after is completely different to what I am getting here. Copy and paste this again and see what I'm doing different. So, round pause is hold on. Yeah, so that part of the math is right. So I'm doing the right thing here. So we have the new pause anyway. Okay, so if I use that position, it's better. So where's this 32 coming from now? We have to be later. We have... I'm doing something wrong. This doesn't make any sense. 1.14 and then it's 1.65. 1.12 and then 1.66. So that's close enough. Y after Y later. How is this number not that number? Huh? Oh, is it because it wraps around? No, but the click happens here. That should be fine. Maybe the same norm angle in there. I don't get it. I don't get it. I don't get it. I don't get it. It doesn't even make sense. Like, this velocity vector is like more than 50, so how is the angular velocity only 32? I'm gonna make this smaller just to make sure. Well, hold on, this doesn't make sense. Okay, now I'm just doing something silly. Oh no, oh no, oh no, oh no. That's a bug. That can't make sense. Okay, so we have 2.19. No, that also doesn't make sense. Then 29. Okay, this 29 makes sense. 2.19 doesn't make sense. 32, and I'm getting... Okay, this is 29, so it's actually kind of close. Why is it so far off? There's no gravity this time because I'm setting ACK to 0. So it should just be normalizing the radius. So and this is just very like the small difference in the value there is causing that. Okay, so now we have the same two positions. New pause and pause later, or these are identical. How am I getting a different velocity? Ah, because pause after is supposed to be new pause. No? Okay, now view later is the same as this one. Yes, I guess I need a new y here because my y is getting calculated wrong. Still off. Okay, so this is taking the relative position and then computing the vector angle of those. So we have the angle is 1.654. Yeah, and y after is what this is using. Y after, y later. Yep, 1413654. Yeah, it's just because this is calculating using the different time step here. Okay, let's do 160 just to make sure. Okay, now you get 370191 is this one. Wait. Does that make sense? I guess yeah, it does make sense. Okay. I guess I need to fix my damping for this to make sense. It just doesn't really work at large angles. So I guess the way the damping is working is it's basically, okay, let's think about doing this in terms of like the actual math. If we take, instead of doing this, right? That's without damping and it's gonna go, yeah, it's gonna go around. So, essentially what's going on is it's taking the current velocity in terms of the like emulated FPS. And it is projecting that linearly onto like a curve. So it's doing this thing, right? So what's the math for that? If you write it out, the inverse operation is basically saying, okay, take the angle, take the the inverse operation is we have y equals cosine of angle, right? And x equals sine of angle. And we're basically normalizing back to y equals 1. Which means we're taking sine of the angle, that's the x, divided by cosine of the angle. And that's how much motion it is doing it, which is the tangent in this case. Does that make sense? No, that doesn't make sense. Hold on. No, that's not how it works. It's multiplying the sine by what am I doing? I'm bad at math. You wanna look so cool? Thank you. You like it? Why am I so bad at math? Wait, this is just a triangle for me. What am I doing? I'm dumb. Isn't it just a sine? This is a sine, right? Sine of the angle No, I'm done. Why am I so dumb? This doesn't make any sense. Huh? Again, no, that means that it's just actually write out the math that it is. Why am I complicating this? You take the x, and that gives you the new length if you add 1 square root. So it's the square root of x plus 1, x squared plus 1, no, x plus 1. No, what am I doing? x squared plus y squared. So x times x plus 1 takes us to the new length. No, it's just arctangent. Ah, yeah, why am I complicating this and stuff? It's just arctangent. It's arctan of yeah, what am I doing? It's just arctangent of where's this? Arctangent. I'm just read them today. So it's velocity divided by emulated FPS, just how much you do on every frame. And then 1. And that's the angle, which is also the angular velocity. Something like that. And still not quite right. That's almost identical. Yeah, it approaches half pi, so it is doing what I want. Okay, let's for a second get rid of this step. And just do a what? Turn this print off. So yeah, my damping isn't working. Obviously doing something wrong. Oh wait, this is the DV, so it's supposed to be the... I think it probably needs to be squared. Maybe? No, that doesn't make any sense. That logic doesn't make any sense. And it's still off anyway. Oh wait, hold on. This has to be hold on. This is acceleration per second. So v2 minus v is how much v has changed in one frame, and so then this is in FPS again. Still wrong. Mhm. That is unhappy. Okay, it goes crazy. Okay, hold on. So, in one time step, we have a velocity per second. Divide by the FPS is the velocity per frame. Take the adjustment. Multiply it again by the FPS. That's the new velocity. Lost in one time step. So V2 minus V is a negative number. And then because that is how much is lost in one time step, but this is the derivative of velocity, we have to multiply by the FPS. Okay, that's a little better. At least it's going down, but not the way I want. You know?
I carry 4 boxes.
Wow, amazing.
Hey.
Hey?
Pizza mitai no.
What's that? Pizza? You mean like a pan pizza?
I went to a mall.
Into a mall?
They are the provider for pizza restaurant. They sell frozen pizza. And I asked for osusume. I don't know what this is. Looks like it's full of little fish.
Uh-huh.
So I'm not sure what this is, but it says crazy pizza. Life.
Can you do this?
What did Nande? 私のこと好きじゃないの。
Transition.
どうして？
There we go. Now I'm just making it so that I can do this. Here.
Yeah.
Hi.
You're not eating my lunch.
I ate most of it. Maybe.
That's less than half.
Okay, fine. I wasn't that hungry.
Okay, that's good for you.
Ah.
I don't want to be holding like high fire pizza.
Put it here. Put it here.
Are you sure it's safe on the glass?
Yes, it'll be fine.
Is it safer on the plate?
If you want to. Go.
It's sardine and whitefish.
Ooh.
I don't know if you'll like it.
I think I like it.
She just said osusume, so I didn't check.
Mm-hmm.
How's your scene going? Still on Jupyter Notebook?
Everything is broken.
Hi, chat. Wait, what? It's still broken? Like, it was
I'm not
more
making
broken
sense
than
of why.
before?
Like, it's not accurate enough, and I'm not making sense of why.
No. Which color is you? Which color is you?
I'm the red and orange.
You're the red and orange, and that's the cyan blue.
If I make the angle smaller, it's probably fine. I know, it's so bad. Oh, wait, I didn't do that. Why am I so silly? Hold on, what's going on here?
Massing, thanks for the super chat. Hi, Cyan.
Thank you for the super
You
chat.
got this, Lina. You got this. Every wrong answer is step to the right answer. Thank you so much. Damn, we have money for the pizza. sumasen.
Okay, hold on. So let me put the original. Wait, why is that not working now? No, because I think. Yeah, so this is pretty close, right?
You can hide me. I'm gonna be cleaning the room.
Okay.
Hi, chat. Damn, I left really quickly.
TV. YH. Okay, so. So how am I doing here? This is city. Okay, I'm doing some math wrong here because that doesn't make any sense. Okay, so the velocity ended up at like 3 radians per second sounds about right. So if it's 3 radians per second, for every frame, it's like 0.05. Sadly, I don't understand the damping in the original thing here. Okay, hold on. Let's actually just turn off gravity because it's gonna make this easier to figure out. And then I need to like add an initial acceleration somehow. How do I do that? Now I'm lost? Oh, wait, because it's not the velocity that causes the damping, it's the gravity. It's the way the gravity is being applied. Like, it does damp. Yeah, it does slow down, but not because of this. That's a different factor. It's the gravity that causes it to slow down. Okay, sorry. Ah. Right. Different problem. And that's why gravity was so important for the weird calculation we had earlier. Okay, hold on. Ah. So the problem is that we are basically pulling the bob down every step. We're pulling the position down. Which, like, isn't even how gravity works, because gravity is an acceleration, but the way they're doing is they're adding a position. Okay, so first let's see if if my math works for this one. Hold on, if I don't do any adjustments. Yeah, because I had this acceleration in there, I forgot about that. Okay, so adjustment, I do the A adjustment. Okay, now it's actually kind of getting there. December damping too much. Let me turn off the prints. So now we're not damping too much. If I don't damp... Sorry, we're damping too little. Still too little, but kind of getting there. Okay, that matches really well. I don't know if that 3 makes any sense though, but how do I make it much faster? Okay, yeah, it's still perfect. Okay, yeah, that damping factor is somehow perfect. I don't know where that 3 comes from. That's a little sus, but it might be because of the way this interpolation works. Yeah, somehow this is exact. Okay, so that part does work. And I suspect the 3 is that. Yeah, the 3 probably has something to do with the yes, so if I do 120, then yeah, it's off. And then if I do the emission FPS is 120 also, because this is what we're running, then it's still correct. Yes. And if I run the FPS on the so this is an important test. If I run this only every second if I percent 2 equals 0, and we do it at twice the simulation speed, and then I set this FPS to 120. Yes, there you go. So this is what I want. Right now, I am running at a faster FPS, but it's still emulating a 60 FPS setup. So it means that my solution is FPS independent. So that does work. Very exact, actually. And now the gravity problem. Okay. So for gravity... Let's do some graphing. So let's say we have the pendulum here. And it has some velocity vector that is going to take it here in the next iteration, which of course it's going to clamp back down. But, you know, this is the angle that it's going to end up in. So what gravity does is it pulls down the position. And pulling down the position means it's pulling down the next vector like that. And then that becomes a new angle. Which in this case is speeding up the pendulum, but it's not speeding it up by the right amount. Because what gravity is supposed to be doing is this. Adding this contribution to the angle. Because it's independent of the current velocity, right? It is projected onto the tangent. But what it's actually doing is this. And that is a smaller angle than this. So that means that what is actually happening with the pendulum is not damping, it's that the effect of gravity is lower the faster the pendulum is going. And that is why it loses momentum. In the other direction, if it's going up, it was supposed to be this effect of gravity. Slow it down. It ends up being this effect. Which again is a larger angle, so it slows it down by more. If we're going down, it speeds it up by less. If we're going up, it slows it down by more. So now how do we calculate that? Essentially, the problem is that we are taking the sine of the... To calculate gravity, we take the sine of the angle, which would be this angle, right? And that gives you the... that gives you this value, right? How much gravity is affecting it. Because we have like a triangle here, right? We have this triangle. Hold on, no, it's not like that. You draw a little color. Let's make this black. So other than the imperfection due to the, you know, the step thing, what we have is we have this this curve, right? Which is whatever it is. And the effect of gravity on this angle is based on this angle here. So I'm doing this right now. This angle. So at this point at the bottom, there's no effect of gravity, and if you go up, you start getting an effect. At this point, I'm still thinking of this wrong. Actually this angle. I confused myself by making this right triangle here. It's this angle, right? So you have that angle here, and the sine is this leg, and so that gets multiplied by gravity. But the effect we end up having here is a smaller angle. So this is actually not quite what I was thinking. But it is what it's doing. Okay, oh gosh, this is so weird. It's... because they add gravity into position, not into velocity. It's so annoying to try to like geometrically make sense of their algorithm, because their algorithm just doesn't make sense. It's okay. Let me try this again. Yeah, okay, so they're basically taking gravity and projecting it against the, yeah, it is multiplied by the sine. That's how much it affects the pendulum in terms of linear change, which then becomes a change in velocity due to the, derivative stuff. But, we can basically say that it is the angle that gravity is being compared against is not the current position. It's like the position times plus the velocity one time step ahead. So what if I do that? So now there's no gravity. Oh, I like that. That looks suspiciously close. What do you know? That's it. That is it. Go. That's how the damping works. Much easier than I expected. It's literally just that. Basically, the bug is gravity is seeing into the future, and that breaks the laws of physics and causes it to lose momentum. So what about the arctan part? What if I don't do that? Okay, that's still necessary to really nail it. But I like this because this is actually now FPS independent. Okay, fine. Okay, this makes perfect sense now. Get rid of that. Now it's good. Now we're good. Now this makes sense. Now this is starting to make sense. The math makes sense now. The math makes perfect sense now. Okay, so now that we have something that is really close, what happens with the jump? Okay, so now that's very off. Oh, but this is all nonsense. Ah, look at that. Now, of course, I don't want to actually do all that crazy math, but now this actually makes sense. Now it all works out. Okay, finally. Okay, finally. Finally, it works. It does the same thing. Okay, good. Okay, that was painful. Now if I do an initial angle, make sure this shouldn't actually change anything, but yeah, it's still good. We still match. They still match. Nice. Decimate it. Yeah, still pretty close. Okay, it's not gonna be exact because of like the way the decimation works. And actually, this makes sense because what I just did here is not adjusting for the decimation. It is correct in the beginning, and then after the jump, it goes off a little. Okay, fine. Nice. Okay. So now, can I make this less insane? I'm gonna make a new cell and clean up a bit. Okay. Okay, if I ignore that stuff and just use the vnew thing that I had. Oh, that's actually pretty close already. So now that I fixed the way acceleration works, it's actually really close. Is it always really close? Not always, okay. Okay, so how do we represent that weird, the way it's doing the X movement? Why is it so small? Maybe size it. Yeah, okay, there we go. Let's try this pizza thing. It's good. Yes. So now, what do we do about this crazy math that's going on here? Oh, I had this. Oh, okay, I had an override there. That's not actually helping. Why is it not doing that, actually? We're so close in the beginning. Why would it be not matching? Possibly just because of the off by one problem we have. I mean, it kind of makes sense, like it's an offset there, right? So I think it's just the probably just the time offset issue. Okay, so here is early, and 4 minus 2 is late, kind of. So it's like somewhere in between, right? Oh wait, 5 minus 3 is correct. What? Huh? Okay. So that's the delta of how this is working. It makes sense because this is kind of looking into the future to calculate the velocity, so it's actually supposed to be like jumping ahead, right? So that does make sense. Strange that it's not linear though, but okay. Okay, so now we have this. Yeah, so this is basically correcting the current position, like retroactively, a few frames in the a few frames later with this double like step thing, right? Okay, how can I make sense of this? So now there's no to the G, does that change anything? Yeah, okay, that messes it up, so we don't need that. Oh wait, I'm still doing the stupid no G thing here, am I? Need to turn that off. Yeah, so if I do that, it's a little bit off. Not too bad though. Yeah, that doesn't actually help. So you program a library. This is a library. This is going to be written in Rust once I have the algorithm done. So what this is doing is, okay, it's taking the rel pause, most of the before is not used. Pause before, takes the pivot now. It adds the previous velocity and the mobility and all that stuff. So this is just a regular iteration. The difference is that it is a regular iteration and then it is normalizing after the iteration. So I should be able to just take all of this out, essentially, and just apply the movement once earlier. And it should be able to just take pause before minus pivot now plus pivot now. Yeah, that's already pretty close. And apparently we still need to be in the past, but okay. Oh, hold on. Now it's really close with Venue. So I can get rid of all the other stuff. So now it actually works. Cur 1 times dy fac. Hold on, so this is actually working now, dy fac. Is it always working? No, it's not. now even this is wrong. Great. Okay, so this is not bad with 275. Is this the same? And this one's good. But because I'm using this hack. And I want to not turn off gravity. Okay, it's still pretty good. But some of them are off now. I've had the gravity contributions a little better on that one. And it's a little bit on this one too. Yeah, this is good enough. Yeah, this is good enough. Okay. So no override based on that, and no velocity overrides. And none of this. Okay, I just replace the iteration with this, because whatever I did, I messed it up, so. What happened now? Hold on, the last X corrects thing is like not what I want. Okay, now this is pretty good. And at 175, not too bad. Okay, so now it's pretty close. Yeah, it's pretty close. Okay, so now we have this. What happens if I use the old algorithm? Not bad. not bad. Still not bad, actually. I can live with that. I think I can live with that. This one's a little off. Yeah, so the other one is much better. So is there anything I can add to add a correction here somehow? Kind of looks like it's the damping thing that I don't have, which... So if I don't do gravity, it will probably be not that different. So maybe it's just that I need the damping here also. Well, this is doing the weird position addition thing anyway. Okay, so what happens if the this is using the rel pause algorithm? What happens if I try to clean this up? Instead of rel pause, if I just say pause before minus pivot now. Yeah, then we're off. think just trying things is not really helping here. Okay, so I had some strange stuff there with the renew. If I do just that without any weirdness. Okay, then this is off. And let's slow it down. No. So the y after is pretty much correct. This is really close to that. It's just the velocity that is not correct. So what if I just delete all this for now? And we're looking for a velocity of minus 18. What I actually ended up with is So the order of operations here was, okay, get the relative position, apply everything, then normalize, and then the velocity is the change in position, which is different to the change in angle because they have a new position involved. So instead of comparing angles, what I really want to do is compare the positions and then convert that to a velocity. Yeah, okay, so this v-pause is roughly the same as this one. And that's supposed to give us the velocity. So if we apply this to the new position, we want to get the velocity of that. So we do it without the h. No, sorry, the velocity is divided by h. But then that gets multiplied by like the at 30 FPS kind of story. Yeah, just use h for now. You can just use AX after for that. AX later is AX after. Yeah, okay, then that would just be dpos times h. No, just dpos. And then we take the arctan of that and say while later. Why is it the same as violator? Does that make sense? It doesn't make sense. Hold on. If we are here in the pendulum, we move it here, and then right, moving it again towards the origin doesn't do anything. So the issue is the error there in the calculations because of the other stuff that gets added through, like gravity and things like that. Hold on, why is curve one not being set? I think I broke something because this was a little close before. Yeah, I broke something. Undo. I thought it was kind of close before. I guess sometimes it is. Yeah, this factor doesn't make a lot of sense. What is dy delta backwards? Okay, hold on. The position delta, we have pause before, pause after. Okay, so back to doing some stuff. I keep redoing the same thing all the time. D pause equals pause minus pause before. Yeah?何が?
Can I eat your pizza? Is it bad?
It's good. Yeah, so the issue is that thing with the angular velocity. That needs to be like if I set it to exactly that. No? Oh, sorry, that is already divided by h. If I add that to the position after, No, that doesn't make sense. Oh. Why after plus this velocity is supposed to be this angular velocity? Why is it not that? No, something's not adding up here. But 942 is this one. Why after? It's close enough. That's x after 0, whatever. What am I doing wrong? I don't know what I'm doing. Now? Okay, thank you.
I'm gonna take this.
Hi.
It's your pizza, okay?
Something is really silly here, because, like, I'm getting this minus 181 from this. And that is, printing velocity and angular velocity. And I know angular velocity is calculated like this. And I know the position. So why am I not getting the same math? Time to copy and paste. So velocity is dpos. It's already multiplied by h here, so that's just dpos. And the FPS is set to 120. Oh, that could be the problem. No, it shouldn't be, because I am... No, yeah, that could be the problem. Hold on. Hold on. Let's go back to 60 FPS. And I was like wildly off. But it's because I copy and pasted this and it's different now. Uh. How is it completely broken now? I get it. 5 before is 4-3, y after is 8-9-3. I mean 8-6-2 here, which like okay. And then getting 6-0-8. I should start drawing the things on the graph. Because now I'm really lost. Mm-hmm. Right. So essentially the issue here is that the if you're just looking at the motion, the angle doesn't actually contribute anything to the motion. However, because they add gravity and other nonsense, you end up with a very strange calculation. Yeah, okay. Here's the problem. We're moving the pendulum, right? So what happens is, this is the original position. The x-axis moves in this direction, right? Let's say it moves some more. Like here. So we have a new angle from the old bob position to the new pendulum. And basically this is like this. So the pendulum was here before we dragged the origin. It ends up here now. Now, the thing is, the old their algorithm says, oh, it moved a ton in this direction, so now that's the velocity vector. So it is going to, the next frame is going to move the same amount. So the next frame is going to end up here. Now the thing is, that's still on the same line. So the pendulum is going to be normalized and go to the same place. However, the problem is that now there's going to be some contribution due to, say, gravity, right? So you would have a vector that looks like that. That's your intended effect, right? Due to gravity. But because of this extra motion here, you end up with this. And so, while in a reasonable engine, your new, your movement due to gravity would be this angle, on this one, you end up with like this angle, which is much bigger. And that only happens in the first time step after the thing gets dragged. Because after that, it's now, the previous position is now, like this weird thing doesn't happen anymore, right? The velocity is what it's supposed to be after that. Why don't I use AI? Because I don't think AI actually really helps you understand things. There are also good reasons why I don't use AI for this specific project. For other parts, it's mentioned in the video description, legal stuff. But I don't really like the idea of, you know, offloading things to a computer, because then I'm just gonna forget how to do things myself. Okay, so with this in mind, with this idea in mind, what we want to do is take the current acceleration vector and this is, and the weird thing is this is going to affect gravity, and it's going to affect a lot of things. We need to like give it one boost worth of gravity. And then also the same for the regular acceleration, the regular motion. This is so weird. Okay. Essentially, I think we can maybe make sense of this. So this is the new position. Pause after, pause before. Okay. And now we have the vector going here. Okay. And now we need to basically apply 1 frame's worth of motion . Okay, yeah, that makes sense. So we're gonna have 1 frame's worth of motion at the simulation rate at emu FPS. Running the derivatives at that. Is this gonna work if I I wonder if I can just call the deriv function. Should be able to. I ended up not using it H here for anything, right? Yeah, I did. Okay, good. I ended up using dx? No, I didn't. Okay, good. And I want to already be running the updated position for this. And now we're just adjusting the velocity. So we keep the velocity for now. Do we keep it or do we? No, we need to at least the velocity is going in this direction. I do need to multiply this times the cosine, I think. Or I just calculate it based on the original angle. That would also work. I think. It's gonna calculate the gravity and stuff based on the new angle. Yeah, it's probably gonna be close enough. Let's try it. So we apply the new position. We calculate the new y later is basically this. And then we want to get the new position of that. Yeah, so we get the difference in position after moving it one time step. And in this case, instead of dx, we want this to be the sim fps, 1 divided by the sim fps. Actually, it's just sim fps here. So this is our new position after that. And then that needs to be applied here. So position later would be position after plus the depause thing plus depause later, and some of this is going to simplify. And then we take the arctangent of that. And it's not really the position, it's just the we just want the relative one, so it's like it's yeah, it would just be AX later plus the depause. Because we have this position here with the angle, and then we adjust it by the depause. It gives us a new angle to get the arctangent of. Okay, that makes sense. So we have the short angles of before, after x, before x, after x later. And we have the adjusted version and y later adjusted. Y later and y later adjust. And it's not sim FPS, it's mu FPS. Okay, so you have y after, y later. What's going on with multiple things there? This is all useless. Right, so you have y after, y later, and y later adjusted. And that essentially gets applied as a velocity change. And this is for mu FPS. Okay, that didn't quite work. Because this has to be multiplied by mu FPS. I guess it's still not quite there. $29 and $20 minus $8.85. The start angle's already a little off, and that's actually going to make things kind of worse for this. You should try a different threshold. How's the angle so far? 138, 118. That's kind of weird. Not supposed to be that far off. Maybe it's decaying too much. Let's just try 120 FPS. Yeah, 120 is a lot closer. still suspiciously off on the start angle, though. Oh, wait, hold on. 324 and then 325 here. That's right. Okay, 325. Which is 319 and 947. Okay, that's pretty close to this. And velocity is a little off. But I'm doing this velocity as a as 160. So let's do this as 120. Ah, there's no temp fact now. No, we don't use that anymore. Where's that? Oh, that's not good. Is it? Oh, it doesn't matter. Okay, we're not doing it anymore. Okay, so this -5 looks about right. And why is it not working? Did I not update it? Okay, so I have a -12 from them and a -5 from me. So something is not quite calculating the velocity right. It could be because of the way I'm doing it based on the angles. Okay. So we're going from 398, 947, 309, 947 to 358, 539. 358, 539, not exactly right. Because we need to add like one iteration's worth of movement to that. Wait, hold on. D curve. Oh, yeah, it's the derivative. Yeah. Okay. So y0 plus current 0. Okay, so now we have okay, I need to print those separately. So we had pause before, pause after 351, 529. And we're looking for 358, 539. That's 353, 532. Yeah, so it does do a bit closer, but not quite. I'm just gonna try the 3 factor there again. 358, 539, 358, 539. Yeah, that 3 factor. There's a magic 3 factor somewhere somehow. Okay, so that 3 factor is helping there. Oh, that looks much better. That magic 3 factor. And now it's pretty close. Okay, that's one that's bad. Is this one of those cases where the length of the movement is almost identical to the length of the vector, so it's gonna be like extremely unstable? I don't think there's much I can do about that. I'm gonna have like I'm gonna put the movement factor here. Yeah, when change and radius are really close, it's just gonna be crazy. And if you make it even bigger, if I make the input change even bigger, it goes like completely in the opposite direction, right? If the change is greater than the radius, then yeah. This is interesting though, because they are actually behaving better than me now. I don't do the adjustment. Yeah, okay, you can see that I did a weird thing, right? I did the jump and then it jumped in the other direction. Let me show this a little closer. One. Still something that doesn't quite add up here. Make the graph a little bigger. Let's turn the pause later. Yeah, so you get the crazy position later. And then you get that like minus 1.89, yeah. Wait, that violator doesn't make sense. Ah, it's after adjustment, yeah. Yes, if I use y new equals y, later adjust. No, that doesn't really help. And that's not really what it's doing anyway. Because this is accurate. The position after this angle after is 1.236, which is that is why later. That doesn't do anything right now. And this also angular velocity is also just about right. Let's also print the other things there. Yeah, the problem is that the velocity change is actually just a step change. And it's supposed to go back. But of course mine is actually using angular velocity, so it doesn't do that. So this isn't going to work like that. I guess what that means is that I don't really want to change the velocity. To that. It's more like it's just one delayed change in position. Yeah, it's a very weird relation, right? It's basically what happens is, okay, if we are going further than the back, like if we end up here, what happens then is that we have, so say we end up down here, right? Now we still have this change in position that happened here, right? Because now this gets normalized, that actually that angle ends up like way over here. Yeah, this is really confusing. That angle ends up like over here then, right? And so now we have another crazy delta angle like that. And it happens again, so then it ends up equalizing on like the third iteration. Yeah, I don't think there's any sane way of emulating this. I mean, this is for all intents and purposes a bug in the original implementation. I don't think we're going to be doing this. It doesn't make a lot of sense. Like, let's say we have this here, right? So you end up with this kind of vector. So then, that's too much actually. Let's do this one. And it needs to be a little longer. So if you put this here, then this pendulum ends up like over here. And then you have this vector. I like the end, like, it would be nice if the end. Ah, yeah, we can do that. So it's like, okay, this went from here to here. And then some whatever motion, right? So it's like, okay, that's the vector that we ended up with, right? And then that vector again gets applied here or something. Actually, this would be eventually like... It looks like this. Then you end up with this rotation actually ends up like here. And then you apply this vector again to this, so then you end up with this pendulum. This plus the whatever happened there, right? So you end up with whatever's going on there. But now you have this other vector, not right? That describes the new change in motion. So then you apply that again. And, you know, whatever gravity thing is going on. And then you end up whatever this is.
No.
I think my conclusion is basically I'm not gonna implement this insanity because it's just too crazy. Then you end up with that, and then finally, like, it does converge, right? You end up with this more reasonable vector going on there. So then that ends up here, and now it's starting to look like, okay, that's just the rotation, right? And it kind of converges there. But this kind of chaotic thing, I don't think there's any reasonable way to implement it in terms of angles. Which is to say, I think I've wasted my time most of today because there's no reasonable way to do this. Like, I already have the code reverse engineered. Like, I already figured out exactly what the cubism code is doing. I'm just trying to figure out if there's a better way of representing it than their very brute force and poorly designed code. And my conclusion is that there isn't. Because there's, like, how do you even define this? Mom? Nani? What's that?
No.
What?
Hmm?
Three? But you have it's all in the living room. All of it is in the...
Are you gonna be downstairs?
I hope so.
Hope so is when. I should sleep first?
I'll be done soon. I'll be done soon.
I'll sleep first.
Fine.
You don't like it? You don't like the
I like
pizza?
it. I'm just too busy.
Do you even know what it is?
Mm.
It's sardine and fish.
I know.
You don't have to.
Hmm.
Bye.
Hi. Yeah, I don't think there's any good way of doing this. So one thing to keep in mind is that so I'm already this part, right, where it ends up here instead of there. That part is already implemented by this adjustment here. So in theory, this should actually work if I just give it this speed. I think. Kind of. So what's going on here? So this part is the same, about the same position after that. And then we end up at like -1,850. And that's where it's completely different. See, that's a good question. Why do we end up here? If the, if the y later just is 1.89, why is SP after not that? And it's not its velocity, though. So theirs actually completely loses velocity in the next iteration, but mine doesn't. Why? Because it keeps going in that direction. And that's... right. This arctangent thing I have going on here only works when the velocity is actually angular. Because it's not here, it doesn't work anymore. So I have this huge velocity here, but it assumes that instead of basically the geometry it's doing is that, okay, if we went this far, that basically means we have a huge velocity this direction, right? And then it loses going here. What actually happened is it went essentially opposite. And then if you keep doing that, it doesn't do anything anymore. I think I give up. I think this is not gonna happen. This crazy jump input angle thing is not gonna happen. Like it is very poorly behaved in the original, and I can't think of a way of simulating this that doesn't involve just literally copying the code. So I'm just gonna test this for small inputs. Essentially just adjusting the new position. And you know what? That's good enough. Maybe do the cosine thing. Where was that? This thing. I know that the read does much, but yeah, you need to simplify the y there. It's close enough. And yeah, that cosine doesn't really do anything. Even in this case where it like slows down the pendulum a lot, it does work. Okay, the cosine isn't helping. Yeah, we're just gonna go with this. I'm gonna use cell and just clean this up a bit. Oh, how do I make it use cell? And then, yeah, there's like a delay of 1 or something like that if you want to really match it. It just means I can just move this after the calculation here. Yeah, and then I can always run it and it still doesn't break anything. And so then I can set a small angle change. It's pretty close. And then we can just kind of simplify this. So that's x, cur x. It's not used anywhere. Anyway, good enough. And then, if we try some other settings, for example, decimate 2, still pretty close. Try with a bit more input. And yeah, still pretty close. I think that's pretty close. Now I really broke it. Oh yeah, because I did something. That's the speaker. Yeah, good enough. Yeah, we're just gonna go with this. We're just gonna go with this. Okay, let's clean up. Okay, I'm gonna take a very quick break, and I think maybe I can even try to implement this really quickly. Maybe it's not gonna take that long. It's not. Just put this into the rust and see what happens. Okay, be right back. I'm back. Okay, time to write some Rust. So let's create a new file here. Alright, first thing we need is a description of the physics system. That has to be the JSON structure. So that has to go here in meta. So that's what the physics tree looks like. So we have abstract. Let's call it vector. Pub x f32, pub y f32. Physics meta has, we don't really care about the counts. We only care about the FPS. And the effective forces. And then we have the physics dictionary, which just has the names. where we use that. Then we have physics setting. There's an ID. And then it has a list of inputs. And then it has a list of outputs and a list of vertices. And normalization. Normalization is position angle. So then we need the input, physics input. This elevator so you can see it. I guess we want the version here too in physics. Oh, that goes in the top. Okay. So each input has a source. And so we need something called like a physics so a physics value, target, and ID. So then the input has a source. So physics. I call these post keys. Let's just start physics target. And weight, type, and reflect. And this is an enum of X or angle. I had some enums here. And reflect. Yeah, type is a keyword. I can just do a sturdy rename. then we need the physics output, which is very similar. Except the type is always supposed to be angle in this case. So I'm actually just going to comment this out. And that just has a vertex index and a scale as extra stuff. Scale. And we need to call the first one destination. Okay, good. So we have the inputs, the outputs, and then the vertices. The vertices have a position, but that's actually not really used for anything. As far as I know, that is ignored, so we're gonna just take it out. And then mobility, delay, acceleration, radius. And then finally we have the normalization section, which has position and angle. And so physics normalization is just going to be position and angle. And then finally we need a physics 3. A physics... We're just going to physics 3. Version... What was I using for versions before? I think I have this before. Yeah, U32. And then we have meta. And that's all there is to that. So I'm gonna go straight to the demo and load, have a physics load thing here. Struct, abstract, physics engine. Setting in config. So we can have like stuff in there for that. So I call this pub function new. And we're gonna go straight and add this to the loader here. Meta, we have display info and physics. So then we need to have a physics engine in here. So let's use Ayagami Physics. So when we load the model here, we would want to say, first set it to none, and then if we have a file, sorry, this is physics 3 as a setting. Let's call this options. Does this build? Let's give this a shot. Let's go to physics options now. Okay, so we're loading at least. Let's go to the engine and start working on this. I think the meta, the FPS is optional. That was added later, so let's make sure that is optional. Not. Okay. So let's make a pendulum. We have a pivot, we have an angle, and we have a velocity. And then we have the pendulum properties. This is stuff in meta here in vertex. Mobility, delay, acceleration, radius. So the physics engine has a set of pendulums. So let's load those in. For each setting, sorry. Each physics setting has a set of pendulums. So this is a physics system. Let's call this system. I need to call this physics everything. System. So it's setting vertices dot into I should just iter. Is there a skip first or something? Yeah, I can skip one, skip the first one. And then we map the pendulums. Actually, I can just iterate for set. Text in, setting vertices, iter. I think like the iter here even. There. So the pivot increases for each pendulum by the radius of the previous one. So then for the pendulum, go simulate dt a new pivot vec2. And this is not itself. And we need to get some reference to the configuration. Yeah, instead of some comparative PS here, I probably just want to have it as a mutable like that. Okay, so for the simulation, we're basically doing this stuff here. If it's compat, how do I get a sign out? Oh, you just did a dot sign? Yeah, basically that. I think just 810 instead of 810 for this. Yeah, just 810 is fine. Does that make sense? No, hold on. No, that's not what I want to do. 810. What's that V2? Does it make sense? Yeah, it makes sense because it's gonna be this. Yeah, okay, never mind. Okay, so that's the derivative function. And then for the simulation, so there's gonna be some extra stuff here to get the angles right. I need to add the input angle or something. I haven't actually added that to this yet. Probably should check if that makes sense because I haven't really done the simulation of that, but I think we can maybe make it work. If the pivot is not equal to the self-pivot, we say, okay, and this is actually cosine sine, but I want sine cosine. Is that a transpose or What? There's no transpose or has to get transpose? There's no way they don't have a simple flip. Really? There's no simple, like, flip? What? No way. Well, I guess I can set it, after is before plus delta. I guess I don't really need to normalize it because I'm just gonna get the arc 10 anyway. So I just need to get delta backwards here. I think that should do it for the pendulum simulation. I guess we want to have the bob here. How do I flip this? There's no way to flip it. Come on, there really is no way to flip a vector. There has to be a way to flip a vector. Okay, I'm just gonna add this because this is pretty silly. There we go. So that should be enough to simulate the pendulums like that. We're missing the angle input, which is gonna be interesting. I guess I should test that first. It's probably not too hard to do though. Yeah, and then if we have this boost nonsense, we need to do a thing. Set initial angle to 0. And then we have this funny broken rotation thing. Which I said I was not going to emulate. I already experimented with that and realized that there's no reasonable way to do that. So we say dA times by 5. There we go. So that's the math there. Yeah, looks good enough. Oh, and this is not angle. This is G angle actually. I guess that's just adding to y, which is only used for that, so I can just add it to the input and not have a separate argument. I guess I said it as a separate one, so it's a little clearer. Okay, so that takes care of the angle, and then the only issue is the angle plus x movement. And so only the first pivot has the funny stuff here. So basically it's this rotation here. occur A. And then we can just do the delta is... That is supposed to be inverted like that, I think. Okay, so now what happened? Now it went very wrong. Huh? I have some food. I have some food. Where's... Why did I mess up here? Why after? I didn't load A. I somehow missed loading A. Okay, there we go. That looks better now. I think I have the thing backwards. Hey, that looks better. Okay, now this is wrong. Position is good. Velocity is not being adjusted. I said we weren't gonna do that though. Something feels a little off. Oh wait, this is no, this is multiplied by the offset. Something's not right here. I'm probably inverting the wrong thing here. This is inverting after the rotation. gonna make pizza? What, you're gonna make pizza again? Yeah, that's kosher now. I think this is correct. Yeah, I think this is correct. curve 0 there. Yeah, that looks fine. It's doing the right thing. It's doing the right thing. What happened now? Initial angle is probably wrong. Yeah, actually, that looks fine. So we have an angle there, and it is applying the right amount of rotation, and if I don't do the broken rotation, it'll be off. Yep. Okay, yeah, that works. And this does work with this one. Okay, so let's implement the pivot stuff. And it's plus delta, which is old pivot minus new pivot. Yeah, which is correct. So it's flipped around. So for simulating the system, we have the dt, and we need the input x, and input angle, and options. So for simulating the system, we do the same thing we do here, which is this. And then this should be not inverted because I'm inverting it here. There we go. That should be enough to simulate the system. And then we need the thing to get the angles. Is there an angle normalization function? I think there's an extension for F32 somewhere. But it doesn't do the angle thing. I don't think that's a thing. Okay. Okay, so now we can get the angle from the system. And that's pretty much it. Now we just need to do the thing where we drive it. Mm. Okay, good. be another pizza?
Told you.
Gosh. Okay. This is the 8 and 2 of that. Edward? You okay? Is it hot? Okay, there we go. Now we have all the systems, and now we just need to figure out the inputs and the outputs. You okay? I see.
That's you.
Hmm?
That's you.
I see.
I wanted to.
Okay, and then we basically do a pop FN apply on a pose. And I have another file that I'm going to kind of steal because that has the stuff to apply the physics. This is what I used for the Godot demo we did. So we're basically copying this function. This is for a physics engine. This is a physics setting, actually, is what this one would be.
Bye bye.
So I think I'm gonna put the setting in here. Actually, target should always be a where's the thing? So string is a with a single value. This needs the parameter data. So this needs to actually do the pose. Key is equal to pose key param ID. And then we need to get at t equals v minus min by that's not max, that's min. Okay, and then we normalize, so... Position and angle. Normalization function. Okay, that should take care of normalizing. And then for each output, oh, vertex index should be a integer, not a float. Vertex index U32. And now in physics here, times input scale. Output.reflect. Okay, looking good. ID is input ID. I need to derive EQ on those. Okay, I think that's pretty good for simulating physics. Now I just did have the update function call it on everything, so for system and self systems iter mat pose dt self dot options, and that is it. Cool. Now, do you think we can make this work? In the demo, we're already learning the physics system. If we have a physics system, basically what we do is we have to change the GUI mode to render on every frame. Render mode. I think there's a thing we can do for that. Or is it eFrame? Actually, I think it does that. I think EQE.rs has a thing. Backend. No, reactive continuous, that's what it is. Where is that? I continuously get a context request repaint. So basically what I can just do is if self dot state dot physics is sum. If we have physics, then request repaint. My tracking just did it silly. Okay. And this context is the agree context. How do I get that? I can do this in logic. Okay, so it makes sense. If we have physics, we can just drive the pose and request a repaint. Yeah, I basically want this stable DT, so it makes sense. We do that, and then to actually get the model updated, I can just draw this unconditionally, honestly. It's gonna do the right thing anyway. Is it gonna work? And I'm gonna have to leave pretty soon, so if it doesn't work, looks like it does not work. It does not. Okay, let's do some printing. And actually, I should set the if we have physics, actually, I should just set the breathe thing. I think it's called parent breathe. I think it's supposed to be something like that. Even that's not working. Is it never calling update or what? Maybe we don't have physics. Yeah, I've not had physics. What happened with the physics? Okay, it's failing to load the physics. Map exhibit string at 920:4. In 20:4. Physics dictionary. As a vec of named entity, isn't it? Ah, now we have something. And it's stuck. We have an infinite loop somewhere? Yeah, it's stuck somewhere. So it worked the first time and then it like died the second time. Why? Weird. I don't really have any infinite loops here, so that's very strange. Like, this is the only one here. I can just turn this off, but, Oh! Okay, now it's broken. Oh, it's probably like a nan or an infinite or something like that. It's probably going into infinity. Whoa, that's crazy. Okay, so it's just a huge number. guess I'm running out of time. I'm running out of time. Wouldn't it be nice if it worked?